Hi, welcome to this course where we'll try to improve your statistical inferences. My name is Daniel Lakens. I'm an experimental psychologist working at the Human Technology Interaction Group at Eindhoven University of Technology. Now, some years after I completed my PhD, I realized that my understanding of statistics was actually not good enough to design a proper study. I joined the Reproducibility Project, which has the goal to reproduce 100 studies in psychology. And when I started to perform the replication study that I would do, I realized that I had to calculate an effect size to perform an a priori power analysis. Now, this is a very basic first step when you design a new study. Whether it's a completely new study or a replication study, it doesn't matter. I realized I didn't really know how to do this, and then I wondered, well, if I don't know how to do this very first basic thing, how can I ever collect informative data? Since then, I've been looking into how to improve the way that we design studies and draw inferences from data. I published some papers on this, and I've realized that improving the statistical understanding of how you do research really makes you a more efficient and better researcher. So I'll share some of the insights I had, and I'll try to prevent some confusion that you might have about statistical tools that we use. The goal of this is to try to prevent you from fooling yourself. As Feynman reminds us, the first principle in doing science is that you must not fool yourself, and you're the easiest person to fool. So I see a better understanding of statistics as a very good way to try to prevent you from fooling yourself. Now, as an experimental researcher, the goal might not be to do statistical tests itself. What you always want to do is to say something about a theory. So the goal of data collection is to first draw statistical inferences and then to draw theoretical inferences. That's what you really want to know. But of course, you need to draw good and valid statistical inferences because otherwise the next step doesn't really work. So let's try to improve this step. There's a reason why psychologists, maybe scientists more generally, are now really interested in improving statistical inferences. And one of the first reasons for starting on this improvement cycle was a study published by Daryl Bem on precognition. Precognition is the idea that we can predict the future. Now, you might believe that this is possible or not, but as a scientist, we should always keep an open mind and look at the evidence. In this case, there was a set of 9 published studies that all showed support for the idea that people could predict the future. There were very simple, basic tasks that were performed that are widely used in experimental psychology. But the tasks were always reversed. So instead of first seeing a picture and then pressing a button to categorize the picture, the task was presented in the reversed order. People first had to press a button, and only then the picture would emerge. So of course, you don't really know what to press unless you can predict the future. And in this set of studies, people were able to perform above guessing average in most of these studies. So after this, maybe some people thought precognition must be real, but other people thought, well, if this can be published in one of the top journals in our field, then maybe we are not drawing the correct statistical inferences from data, because it seemed unlikely that this was true. There has been more criticism in the scientific literature on how we draw inferences from data. Now, there are some people who even go as far as to say that most published research findings are false. Is this true? What do you think? Do you think that most of the scientific literature is false or not? I think the answer is we don't really know. We can try to estimate it, but we don't really have an accurate number. It's more important, probably, to try to improve the way that we do research to prevent this from continuing on, so that in the future we know that the data that's generated and the conclusions that are drawn are most likely to be correct. There are some problems in the scientific literature at the moment. We know that many of the sample sizes we collect are too small, so we have underpowered studies. We know that people are very flexible in how they analyze data. So this leads to a lot of flukes, random findings that are actually not true, but that people interpret as a true effect. And we know that there is strong publication bias. People share findings that show an effect, but they don't share findings that do not show an effect. And all these things make it very difficult to conclude whether published findings are reliable or not. And the goal in this course is to try to give you some tools to try to answer this question better, given that there's publication bias, flexibility in the data analysis, and low-powered studies. So first of all, we'll try to make sure that you can draw better statistical inferences. To achieve this, we'll talk about p-values and how to interpret them, report and calculate effect sizes and confidence intervals, but also discuss alternative ways than frequentist statistics, such as Bayes factors or likelihoods. The second goal is to enable you to design more informative experiments. To achieve this, we'll talk about how you can control error rates when you design studies, how you can efficiently run high-powered studies, but we'll also focus a little bit on theory construction. Another goal is to evaluate the evidence in the literature, given that there is publication bias. We'll talk about p-curve analysis and we'll discuss publication bias and some ways to identify this in more detail. Finally, an important goal is to facilitate cumulative science. Of course, we try to improve our knowledge. How can we do this the best way? We'll talk about how you can perform replication studies, the importance of pre-registration and the benefits of using pre-registration, and the importance of adhering to open science principles in your research. Accompanying these lectures are assignments, and these assignments are really hands-on and in-depth knowledge. The goal is to learn mainly through simulations. I'm not a big fan of teaching through formulas myself. If you're interested in that, you can easily look up the literature and I'll provide references where these formulas are discussed. But in these assignments, we'll mainly rely on performing simulation studies and just seeing what happens in the long run when you would perform hundreds of thousands of studies. Personally, I found that really informative when I tried to understand statistics myself. We'll use R, which is free software. You don't need to have a very good understanding of how R works. We'll typically use very simple examples where you can just run the code, maybe change one or two numbers. That's really all you need to know about how R works. Now personally, as I started to get a better understanding of statistics, I felt much less uncertain and much more able to draw correct inferences from the scientific literature and to design studies that would yield informative results. I really think that if you want to be a good researcher, it's important to invest some time in learning how to draw better inferences from your data. And it can be remarkable fun getting this better understanding. If you want to reach out to me, you can contact me at Twitter with any questions or comments you might have. For now, let's get started. In this lecture, we'll talk about three different ways in which you can draw statistical inferences from your data. We can see that there are three main questions that you can ask, which are all related to different statistical approaches. So let's take a look at each of these in turn. Now, in statistics, we'll see that there's basically one truth that we all try to figure out. But the paths towards this truth, there are many different ways to try to do this. One useful metaphor that I think can help you think about these differences is if we look at Hinduism, where there are three ways to reach enlightenment: the Karma Yoga, the Jnana Yoga, and the Bhakti Yoga. Now, if you see what the Hinduist book Bhagavad Gita says about this, this is basically a path of action, a path of devotion, and a path of knowledge. And I think there's a nice relation to make between these three paths and three questions that you can ask if you do statistics. Now, Royal talks about these three different questions that one might ask, and he differentiates between what should I do, what should I believe, and what's the relative evidence. And we see that these are three different statistical approaches that we can use to draw inferences from data. The first is the path of action. The path of action uses rules to govern our behavior, such that in the long run we won't make a fool out of ourselves too often. Now, this approach uses p-values and alpha levels to either make a decision to reject the null hypothesis or to accept the null hypothesis, or if you want to, remain in doubt about whether the alternative hypothesis is true or not. This is a rule to govern our behavior in the long run. It's important to keep in mind that this doesn't tell you anything about one single test that you're performing. So any current test might be either true or false. We don't know, but what we know is that in the long run, there's a certain percentage of the time that will be correct. So this is the main goal of the path of action, making decisions about what you should do. The path of knowledge, the second way, focuses on likelihoods, and it tries to answer the question what the likelihood is of different hypotheses given the data that you have collected. Let's take a look at this situation where we flip a coin 10 times. This is an old Dutch guilder from when I was young. And we see that there are 6 heads and 4 tails. So if you flip this, if you flip a coin 10 times and this is the data that you have observed, you can ask yourself the question, is this coin biased or not? So what is the likelihood that this is a fair coin, where every option comes up 50% of the time, or what's the likelihood that this is a biased coin? Now we can plot the likelihood function given the data that we have observed. Let's take a look at the likelihood function. So this curve tells us all the likelihoods of different hypotheses given the data that we have. Now we've observed 6 heads, so you can see that this, according to the likelihood function, is the most likely possibility. But we can also calculate the likelihood ratio. How much more likely is the data that we have given a fair coin? And we see that this is not very impressive. The likelihood ratio is supposed to be 1 if there's no difference between different hypotheses, and this is pretty close to 1. Later on in the course we'll talk about how you can really calculate these things. The last option is the path of belief. Now we have flipped a coin 10 times and we saw that it came up heads 6 times. Now if you see this, do you really believe that the coin in the long run will come up heads 60% of the time? Now that seems rather unlikely. You have previous beliefs about coins and you have a very strong belief that most coins are fair. So in the long run you might say, well, I've observed this one time, there were 6 heads, but I don't really believe that this is what I'll see if I continue flipping the coin. I think still that 50% probability of heads is what's going to happen if I do this over and over again. So you see that in this case, the data did not really change your prior beliefs. And this path is known as Bayesian statistics, which allows you to express evidence in terms of the degrees of belief. So how much do you believe in a certain hypothesis? So these 3 different paths, the path of action, the path of devotion, and the path of knowledge, we can sort of make a relationship to Nyman-Pearson statistics, which is the path of action, using alpha levels to decide between the null hypothesis and the alternative hypothesis. Bayesian statistics, where we talk about the degree of belief in a hypothesis. And likelihoods, which tell us something about relative evidence between different hypotheses. Now, in the history of statistics, we see that there's a lot of discussion going on between different sides in this debate. And if you want to know how nasty science can get, then I invite you to take a look at the discussion in the scientific literature between this person on the left, Jerzy Neyman, and the person on the right, Ronald Fisher. Now, Jerzy Neyman is about the path of action, and Ronald Fisher uses p-values in a slightly different way, p-values as a measure of evidence. Now, Ronald Fisher is a genius, one of the few geniuses that we have in science. He's not only a godfather of statistics. He worked a lot on introducing analysis of variance, for example. But he is also a very respected scholar in the field of biology, where he did groundbreaking work as well. So this is no doubt a very smart individual, but there's a lot of debate about the way that he uses p-values to draw inferences from your data. So if there's a discussion between these 2 individuals, you can say, well, the Nyman-Pearson approach to inference is definitely the best way, the most coherent way to draw inferences from data using alpha levels and the p-value. So Neyman would be really happy, say, haha, after all these years and this intense discussion that we have, I have won. My way of doing statistics is the only logical approach to draw statistical inferences. On the other hand, Fisher might not be too sad. He might say, oh, forget it. No one knows who you are, which is in general true. I think not a lot of people have heard of the Nyman-Pearson approach of statistics. And he would be pretty happy that everybody uses p-values in, well, arguably not the optimal way, but at least the way that he proposed. And, well, he gets a lot of respect for this. You might not know this, but the F distribution, the F value that you calculate in an ANOVA, is actually named after Fisher in his honor. All right. So these 2 sides are debating, but now we see that Bayesian statistics is on the rise in recent years. This is Reverend Thomas Bayes, or, well, actually probably not. This is a picture that's circulating. That might be him, but it's doubtful that it's actually him. Nevertheless, we'll use it in this course to illustrate the Bayesian perspective. And he would say, gentlemen, stop fighting. Who cares about these frequentist approaches to statistics that you think are important? Because everybody in the future will use Bayesian statistics anyway. We can see whether that's true or not. And maybe Nyman would respond, well, I don't have a very high prior that this is ever really going to happen, which of course is a slight joke because he's using prior information to draw an inference in this case. And you see that when there's a discussion between Bayesian statistics and frequentist statistics, all of a sudden, of course, these two become perfect friends. They say, of course, very good joke, and they will be in agreement about the way to do statistics. Now, the third approach is the likelihood approach. It's not very popular at the moment, but likelihoods underlie Bayesian statistics. And the difference between likelihoods and Bayesian statistics is that likelihoods do use the relative evidence that's present in the data, as Bayesian statisticians do, but it doesn't rely on this subjective prior. One of the proponents of this approach is Rich Royal, and he might say something that nobody really cares about your subjective opinion when you draw inferences from data. So you should ignore this subjective prior and only rely on the likelihood. To which Thomas Bayes might say, oh come on, don't be such a nuisance. Nobody even knows what likelihood paradigm is. And at this moment this might be true, but we'll see that you can use it for certain useful things later on in these lectures. Now it's very important to realize that in this debate, which sometimes feels a little bit like Microsoft versus Apple, there's always this clash between two sides, and people will start to argue vehemently between these two different approaches. For you, it's very important that you can use whatever answers your question. And that's really the main point. It's not either or. You can even combine these approaches if you want to. So the important take-home message here is that there are three different approaches in how you can draw inferences from your data. These all answer a question you might be interested in. And the main thing is that you realize that there are these different approaches, so you can ask the question that will give you the answer that you want. If you read articles in the scientific literature, you will often see people report p-values when they report statistical tests. P-values are widely used, and it's important to understand what they mean. They're also widely criticized because people often misinterpret p-values. So in this lecture, the goal is to understand what they mean and how to correctly interpret them. When we talk about p-values, the first question we should ask ourselves is, why are they so popular in scientific articles? Well, there's a reason for this, and Benjamini expresses it quite nicely here. He says, in some sense, it offers a first line of defense against being fooled by randomness, separating the signal from the noise. So this is what p-values allow you to do. When you interpret your data, you might be very likely to interpret data in favor of the hypothesis that you have, even when the effect might be only slightly in the right direction. The risk is that you're fooling yourself. You might be too likely to declare that something is going on when you're actually looking at random variation in data. So p-values are one way to prevent you from fooling yourself. P-values tell you how surprising the data is, assuming that there's no effect. And we'll look at all these aspects in more detail. What surprising means, why they're statements about the data, and why they're built on the idea that there's no effect. Now, some people say that p-values are more accurately explained as what you use if you don't know Bayesian statistics yet. In Bayesian statistics, people don't use p-values. And I still remember when I was doing my own PhD that I had this confusion about whether I should use p-values or Bayesian statistics. My understanding was more or less that I realized there was some problem with using p-values, and Bayesian statistics might be preferable, but most people didn't use Bayesian statistics, so it was probably fine to just continue using p-values. Now, I think it's fine to use p-values, but you should interpret them correctly. So that's the goal in this lecture, to prevent this confusion in you and to make sure that you'll use p-values correctly if you decide to use them. Let's start with a practical example. Let's say you want to do a study where you examine the influence of calling while you are driving. Does being on the phone when you're in your car increase the risk of getting into an accident? You might design a study where half of the participants drive around a city while they're on the phone, and the other half of the participants drive around but they're not on a phone. You want to see if there's a difference, maybe in the number of people that they hit while they're driving through the street. Or maybe your ethical committee doesn't allow you to do this, and you're better off using a driving simulator to study this. Now, if you've collected your data, you counted how many people get hit by a car, either by people who are on the phone while they're driving or people who are not on the phone, then you can look at the difference between these two conditions. Now, this difference is never exactly zero. There's always some number far after the comma that makes a difference. So let's say the difference you observe is 0.11, a mean difference. Now, how should you interpret this mean difference? There are two options. A, what you're looking at is probably just random noise. There's always some random noise in your data. Option B, this is probably a real difference. This is something that you should take seriously and at least examine further in future studies. So which of these two is true? Well, we can use the p-value to differentiate between these two options. From the data that we have, we can calculate means, standard deviations, and we know the sample size that we have. We can use these parameters to calculate a test statistic and compare this test statistic against the distribution. You can use many different types of distributions. If you examine precognition, you might want to use a paranormal distribution. But most often people just use the normal distribution. So this bell-shaped graph is something you might have seen before. And there's something you should note here, and that's that this distribution is centered on 0. And when we talk about the p-value being data that is surprising, assuming the null is true, the null hypothesis is true, this is what we mean. We look at a distribution centered at 0. Now you can see that most of the data in this case, let's look at 95% of the data, will fall between two critical values. And these critical values, you might have seen this number, 1.96 and minus 1.96. These are critical values if you want to use an alpha level of 0.05. If data falls between these two values, it's not surprising. Assuming that the null hypothesis is true, most of the data will fall between these two critical values. But sometimes we might see a data point that's more extreme than this. And this is a surprising finding. This is surprising data whenever the mean difference, or the test statistic that's computed from this mean difference, is in one of the two tails of this distribution. So whenever we find data that falls in these tails, it's surprising, and we might want to examine it further. It also means that the p-value is smaller than 0.05. The formal definition of a p-value is the probability of getting the observed or more extreme data, assuming the null hypothesis is true. Now, I highlighted the word data here. I think it's important to realize that we're talking about the probability of observing data. A p-value is the probability that you'll observe some data, but not the probability of a theory. This is a very common misunderstanding. People often want to make a statement about the probability that a theory is true. But when you calculate a p-value, all you can do is make a statement about the probability of the data. Now, if you make this mistake, you're in good company. Let's take a look at this example from quantum physics, where a physicist talks about the probability of observing a certain spin between quantum particles. So this is a study where they measured the spin in a particle that was floating around somewhere in Delft, and another one that was floating around somewhere in Amsterdam, in the Netherlands. And these two particles spin together. They have some sort of relationship. And this relationship, based on the data, was statistically significant, with a p-value of 0.04. Now, some physicist is interviewed about this finding, and this physicist concludes, in other words, there is a 96% probability they won the race. So this person is making a mistake here, because with won the race, this person means there's a 96% probability that the theory is correct. But this is a statement about a theory. It's not a statement about the data that you have observed. So it's comforting, maybe, that a quantum physicist, which sounds like you're supposed to be really smart, also makes this misinterpretation of what a p-value means. After you have observed a p-value that's smaller than 0.05, for example, an effect is not 95% likely to be true. Think about precognition research. Let's say that I present one study to you where you find a statistically significant effect of precognition. After this, do you really think it's now 95% probable that precognition exists? Probably not. You cannot get the probability that the null hypothesis is true given the data from a p-value. If you look at the two statements below on the screen, you see that the probability of the data, or more extreme data, assuming the null hypothesis is true, is not the same as the probability of an hypothesis given some data that you have observed. These two probabilities can differ widely. If you want to know the probability that a theory is true, you need to use Bayesian statistics. Bayesian statistics is the only approach that will allow you to make statements about the probability that a theory is true. What happens if you do a study and your p-value is larger than 0.05? Well, first, of course, you spend a lot of time and effort on collecting this data, and maybe you hoped to find a statistically significant effect. So the first thing you do is cry a little. You're a little bit depressed. That's okay. But after this, how should you interpret this data? Well, all that we know when the p-value is larger than 0.05 is that the data we have observed is not surprising. That's all. It doesn't mean that there is no true effect. There might very well be an effect, but you just didn't have enough participants in your study to detect this effect. Remember that you need large samples to statistically detect a small effect. So just because your p-value is larger than 0.05 doesn't allow you to conclude that there is no effect. There might be a very small effect. You don't know. Personally, I try to think of a p-value larger than 0.05 as mu, which is a concept from Zen Buddhism. In Zen Buddhism, there's a famous saying that goes like this. A monk asked a Chinese Zen master, "Does a dog have a Buddha nature or not?" So you might expect a yes or no answer here, because that's also how the question is phrased, yes or no. But instead, the Zen master answered mu, which basically means I'm unasking the question. It's negating the question that's asked. And whenever you find a p-value that's larger than 0.05, you might feel the tendency to say, so is there an effect or not? But whenever the p-value is larger than 0.05, you can't answer this question. So you should just answer mu. So how do you use p-values correctly? The first thing to understand is that p-values can be used as a rule to guide behavior in the long run. You can calculate them for every single study, but they only work in the long run. Let's take a look how. If you use the decision rule whenever the p-value is smaller than the alpha level, so this is your type 1 error rate, which is often set to 0.05, you can act as if the data is not noise. Now this word act is very important. It's independent of what you believe is true, but all that you know is if you use this decision rule in the long run, you won't say that there is something when there is nothing more than 5% of the time. Alternatively, when the p-value is larger than the alpha, you can remain uncertain or act as if the data is just noise. So these are rules that you follow in the long run. When you act as if there is an effect, whenever the p-value is smaller than 0.05, in the long run, you won't be wrong more than 5% of the time. Now, this is an interpretation of p-values as proposed by Neyman. And it's often used. Let's take the discovery of the Higgs boson as an example. If you remember, during the press conference about the Higgs boson, researchers were talking about whether the 5 sigma threshold was passed. And 5 sigma is used as a threshold to declare something a discovery in physics. Now 5 sigma is basically a p-value smaller than 0.00000003. So based on this idea, we can act as if the Higgs boson is true. Every now and then, of course, we'll be wrong. With such a high threshold for an error, we'll only be wrong in one of many billions of parallel universes. So there's one parallel universe where people spend the time and effort to build a Large Hadron Collider to detect the Higgs boson. And they declared it was statistically significant, so it was there, but they were actually wrong. But with such a high threshold, this of course rarely happens, and we can be pretty safe that there is a Higgs boson and we didn't make a mistake. When you interpret p-values and you want to write something about what you found, you should not write, "We found a p-value smaller than 0.05, so our theory," because if you do this, you're making a statement about a theory based on a p-value, and you shouldn't do this. The correct way to discuss a p-value smaller than 0.05 is to say, "We found a p-value smaller than 0.05, so our data." You make a statement about the data because that's what the p-value relates to. You might say something like, "So our data is in line with some idea that you want to test." Whenever you found a non-significant result, a p-value larger than 0.05, you enter what's known as a degenerative research line. You made a prediction, but it doesn't hold up, so you have something to explain. Now, one explanation might just be random variation. P-values vary, and even if you have examined a true effect, every now and then you'll observe a non-significant result. So you might just say, "Everything's fine, this happens. If I do another study that's exactly the same, you'll see that it will pan out and my prediction will hold." Other times you might need to say, "Well, the effect that I predicted might be smaller than I expected." So you do another study, but it's larger, and then you show that the effect is really there. Nevertheless, whenever you find a non-significant result, there is something to think about. You have to explain it in some way. One way might be, if you do a lot of studies, every now and then you'll find a non-significant result, but then you need a lot of studies to support this. Other times you might say, "I have to do the study in a slightly different way," and you can use this change in the paradigm to develop a progressive research line. Remember that p-values vary, so always think meta-analytically about p-values. This is also recommended by the statisticians who talked about p-values in the very beginning. For example, this is a quote by Neyman and Pearson. "Statistical tests should be used with discretion and understanding, and not as instruments which themselves give the final verdict." So if you calculate a statistical test, that's only one thing that should go into your reasoning to decide whether this is a true effect or not. Always think more about a study. P-value might be a starting point, but you also want to look at effect sizes and other studies that have been done. Fisher similarly says that a single p-value is not enough to declare some discovery on. He says, "A phenomenon is experimentally demonstrable when we know how to conduct an experiment which will rarely fail to give us a statistically significant result. So we have to repeat the experiment multiple times." He also says, "No isolated experiment, however significant in itself, can suffice for the experimental demonstration of any natural phenomenon." So he's saying that we should see a single p-value maybe as an invitation to explore this effect further, but it can never be enough to declare something a scientific fact. So we always need to do several studies, and p-values can guide us in the long run in which studies we might want to do. So at the end of this lecture, let's take a look at the p-values that you can expect when there is a true effect, and the p-values that you might expect when there is no true effect. Now, I never really realized how p-values are distributed across studies when you do a lot of them, and I think it's very important to understand this for the correct interpretation of a p-value. So take a moment to think about this. What kind of p-values would you expect when there is a true effect? What kind of p-values would you expect when there is no effect? Let's take a look what really happens. When there is a true effect, the p-value distribution depends on the statistical power. Let's take a look at the visualization of this. In this graph, you see the p-values for 100,000 studies, where every study had 50% statistical power. This means that it's 50% probable that we'll observe a p-value that's smaller than 0.05. If we look at the p-value distribution, we indeed see that it's much more likely to observe small p-values than it is to observe high p-values. And if we look at the leftmost bar, we see that indeed 50,000 of the 100,000 simulated studies yield a p-value that falls between 0 and 0.05. Now we might want to increase the statistical power a little bit. You see that with higher power, we have basically pushed more of the p-values below the significance threshold of 0.05. Here we have 80,000 of the 100,000 simulated studies that yield a significant effect. If we increase the statistical power even more, to 95%, we now see that most of the p-values that we'll observe, given that there is a true effect, will fall below the significance level. So which p-values can you expect when there is no effect? I really never knew this myself. I thought that p-values might be distributed in a way that if there's no effect, we'll see a lot of very high p-values. Or I thought that it's possible that maybe they're distributed as sort of a normal distribution. But instead it turns out that when there is no effect, p-values are uniformly distributed. Every p-value is equally likely. And it also makes a lot of sense if you understand it. In this case, we have simulated 100,000 studies where there is no true effect. And you see that no matter where you look in the distribution, low p-values or high p-values, they're all equally likely. Now this makes sense because in this way, when there is a uniform distribution, it means that 5% of the p-values that we observe when there is no effect fall below the 0.05 threshold. So when there's no effect, we have a 5% probability of making a type 1 error, of saying there is a significant effect when there's actually nothing going on. So here you can see this small type 1 error rate highlighted in red. So this is what it means to make a type 1 error. The reason that it's 5% is because there's a uniform p-value distribution. If you would increase your alpha level to 0.10, there's still 10% of the p-values that fall below 0.10. To conclude, it's important to understand how to correctly interpret the p-value. Its use is often criticized because people incorrectly interpret what p-values mean, and I hope that after this lecture, you won't be one of them. One of the three approaches to drawing inferences from your data was the path of action, the Nijman-Pearson approach. In the Nijman-Pearson approach, the main thing is trying to control the errors when you draw inferences from your data. When you say, yes, I accept the null hypothesis, or I will reject the null hypothesis, controlling the amount of times in the long run that you'll make a mistake. Now we talk about this in terms of the type 1 and the type 2 errors that you can make. In the goal of error control, what you try to do is prevent making a fool out of yourself too often in the long run. And I think this is a very useful thing to try when you draw inferences from your data. Now let's take a look at an example. Let's say you're walking down the street, you come across this person, and you have some suspicions that this person might be a vampire, but it could also be someone who is not getting enough sunlight. You have to make a decision to either stake or not stake this individual, and this person can be a true vampire or it can just be a random person on the street. So we see that there's a possibility that you'll correctly identify this person as a vampire and stake them, but you can also make an error. You can make two types of errors, and type 1 error is, well, this is a vampire when actually it's not a vampire, and in this case you would stake an innocent person. The second type of error that you can make, the type 2 error, is saying that this is probably not a vampire when it actually is a vampire. And in this case, you're probably going to end up dead because this vampire is going to suck all the blood out of you. Let's take a look at some definitions when we're talking about this topic. So first, we have to define the null hypothesis and the alternative hypothesis, which we will often indicate with H0 and H1. It's important to keep in mind that the null hypothesis doesn't necessarily need to be the prediction that the difference between certain conditions is exactly 0. Think about flipping a coin, in which case the null hypothesis is probably that there's a 50% probability of flipping heads and tails. So the null hypothesis can be anything, but very often it's the idea that there's no difference between two experimental conditions. The alpha that we use is the probability of a significant result when the null hypothesis is true. And this is the definition of a type 1 error rate. And you're free to set this alpha at any level that you want. A very often used level in psychology is 5%, but we already saw that in some fields like physics it's very common to set a much lower type 1 error rate. And you can also think about areas such as medicine, where it might be useful to set a much lower error rate as well. The beta is the probability of a non-significant result, given that the alternative hypothesis is true. And this is known as a type 2 error. So this is the probability that you'll say there's nothing going on here, when there's actually a true effect to be observed. If we look at the difference of 1 minus the beta, this is the probability of a significant result when the alternative hypothesis is true. So this is the statistical power. When you design a study, 1 minus the type 2 error rate is the probability that you'll actually find a result if there is a true effect to be found. Now remember that Nyman thinks that these error rates are frequentist concepts, so they apply to the long run. Now in any single study, there's either a true effect or not. You are right or you are wrong. But these error rates are about long run frequencies. So you can be 5% of the time you can make a mistake. But in any single study, you've either made a mistake or not. It's important to think about this in the long run. So if we do many studies, how often will you make an incorrect conclusion? Because we have these two situations where the null hypothesis is true or the alternative hypothesis is true, and you can either observe a significant effect or you'll find a non-significant result, we can divide these options into these 4 cells. And here we can see that when the null hypothesis is true and you find a significant effect, you made a false positive, a type 1 error. You said there is something here when there's actually nothing. When the null hypothesis is true, you can also correctly say that there's no true effect, which we call a true negative. Now when the alternative hypothesis is true and you find a significant effect, that's a true positive. Something is going on and you correctly identified it. You can also draw the conclusion that there's nothing going on when there's actually a true effect, and we call this a false negative. Now remember that in any single case, you're either sampling from a true effect or from a false effect. So you're in one of 2 parallel worlds. Either there's no true effect, and then you can only make false positives or true negatives. Or you're doing research where there is actually a true effect, and then you can only make a correct conclusion, a true positive or a false negative. Now let's take this understanding of type 1 errors and type 2 errors and true positives and true negatives to think about what's most likely to happen in your next study. I'll describe a typical situation, which I think is fair and describes many of the studies that we do. Let's say that you don't really know if there's a true effect or not. The null hypothesis might be true, the alternative hypothesis might be true, and both are equally likely. Let's give them both 50%, we just don't know what's going to happen. We'll also use a type 1 error rate, the alpha, of 5%, which is very typical in most research. And we'll aim for statistical power of 80%, which means that there's a type 2 error rate of 20%. If there is a true effect, we will not observe it in 20% of the time. That sounds like a lot maybe, but this is actually a very recommended power to aim for. So in this specific situation, let's assume that this reflects what you want to do. You use this type 1 error rate and you actually exactly meet this statistical power. You have 80% power in your next study. You never really know, but let's assume that this is the case. Think a moment, what's the most likely to happen? Will you find a significant result or a non-significant result? Make a false positive or a false negative? Now let's do the math and see what really happens. So as we said, there's a 50% probability that the null hypothesis is true, and there's a 50% probability that the alternative hypothesis is true. Remember, we just didn't know what was going to happen. We have a 5% type 1 error rate and a 20% type 2 error rate. So we can use these numbers to calculate the probability of each of these 4 cells to happen, and of course they should add up to 100%. Let's first assume that the alternative hypothesis is true. We're examining a true effect. The probability of finding a significant effect equals the statistical power that we have, which is 80%, and it's 50% probable that the alternative hypothesis is true. So we can multiply 80% by 50%, and we find that it's 40% likely that we'll conclude that there's a true effect, a true positive. It's also possible that we find a non-significant effect. This will happen 20% of the time. Multiplying 20% with the 50% probability of the alternative hypothesis being true gives us a 10% probability of making a false negative. Now let's move over to the situation where the null hypothesis is true. Here we have a 5% error rate. We can multiply this 5% times the 50% probability that the null hypothesis is true, and in 2.5% of the time we'll conclude that there's a false positive. We'll say that there is an effect when there's actually no effect to be found. And now we come to the most likely outcome in this very typical situation, a true negative. There's a 95% probability that we'll conclude that nothing is going on, multiplied by the 50% probability that the null hypothesis is true, which gives us 47.5%. So that's the highest number of these four possible outcomes. Now this might be surprising that if you do a new study and you don't know whether the null is true or the alternative is true, you use the recommended alpha level and the recommended statistical power, then the most likely outcome of your next study is a true negative. Nothing is going on, and you'll correctly conclude that nothing is going on. So you might be surprised that the most likely outcome is a true negative, and very often you're interested in finding a significant effect and finding support for the alternative hypothesis, saying there is a true effect and correctly concluding that there is a true effect. So how can you improve these probabilities on the previous slide? Well, there are different options. Let's take a look at what works best. You might say, the problem here is probably that I only had 80% power. When there is a true effect, I only had an 80% probability of finding an effect when it's there, and I need to increase my statistical power. Now in this slide you can see the red numbers, and we have increased the power to 99%, which means that almost all of the time you correctly conclude that there is an effect when there is a true effect to be observed. Our true positive rate has indeed increased, but not so much. You can see that now it's about 94.5% likely that you conclude there's a true positive. It is now the most likely outcome, but it's not ridiculously high. Another idea you might have is say, well, probably the false positive rate is too high. Let's reduce the false positive rate, set it at 1%. So type 1 error is now 1%, and you can see where changes occur. Now, of course, the difference is only in the situation when the null hypothesis is actually true, because you can only make a type 1 error if the null hypothesis is true. So we see that there's a reduction in the number of false positives from 2.5%, now it's only 0.5%, but still, true negatives are most likely to happen. So this all doesn't really help. So what's the most important thing to do if you want to improve the probability of finding a true positive? What you should do is examine hypotheses that are likely to be true. The biggest problem here is this 50-50 prior probability of the null and the alternative hypothesis being true. We can see that if it's about 90% probable that we are right, that our hypothesis is 90% likely to be true when we start data collection, you can see that the probability of a true positive increases sharply. Now, I always use these calculations whenever a master's student enters my office and says, I have a crazy idea. I don't know if it's true or not, but this is my passion, this is something that I really find interesting and I want to examine it. I always say that's perfectly fine, but I don't know if the hypothesis is true or not. It's 50-50, could go either way. So realize that the most likely outcome of your research is a true negative. If you're interested in finding support for the alternative hypothesis, the best thing you can do is examine studies that are, or examine hypotheses that are most likely to be true. Now let's use a slightly different way to think about these type 1 errors and type 2 errors and true positives and true negatives. This is an illustration of the null hypothesis and the alternative hypothesis in terms of normal distributions. You can visit this website and play around with this visualization if you want to. Let's look at all the different components here because there's quite a lot of information. Now the white bell-shaped curve is the situation when the null hypothesis is true, when there's no true effect to be observed. you can see that it's centered at 0. So this reflects the situation where the null hypothesis is true. There's no true effect, but there's some random variation. Now if we take a look at the light blue bell-shaped curve, this is the distribution when there is a true effect, and in this case there's a true effect of a specific size, namely 0.35. We'll talk about effect sizes later in the course, but for now you can see that the likelihood of finding effects that are large is much more likely under the alternative hypothesis. And under the null hypothesis, you will find effect sizes that are 0 most of the time. There's a certain critical value that we often use. It's also illustrated here, and in this case this equals a p-value of 0.05. So this is the critical value, your type 1 error rate. Now given this cutoff of the two distributions, we can make a division between the 4 cells that we saw earlier, but now we're visualizing it in another way. If we look at the white bell-shaped curve, the white area reflects the true negatives. There is no true effect to be observed, and we'll find it a lot of the time. We can also make a false positive. This is still part of the distribution of the null, so the white curve slowly moves towards this red area that you can see with the arrow of the false positives pointing to it. These are situations when we observe an extreme result when the null hypothesis is true. We're saying that there's something, but we're actually making a type 1 error. Now let's switch our attention to the light blue area. You can see that this falls on the right side of the critical value. So in this case we are observing p-values that are smaller than 0.05, and we are correctly saying that there is an effect. We're observing a significant result and there is a true effect to be observed. So the light blue area corresponds to the true positives that we'll observe. Sometimes we'll conclude that there is no effect when we're actually sampling from this reality where there is a true effect. And this is illustrated in the dark blue area. These are false negatives. The values we observe are not extreme enough to lead to a p-value smaller than 0.05. So these are false negatives. Now an important question when you're designing a study is which error rates should you aim for? I already mentioned that the alpha level and the beta that we often use is an alpha of 0.05 and a beta of 20% or a statistical power of 80%. However, statisticians themselves say you should not use these benchmarks. You should think for yourself what the best choice is. Nyman himself talks about it in this way. Is it more serious to convict an innocent man or to acquit a guilty? If you're convicting an innocent man, this person has done nothing, but you're saying this person has done something. So this is a type 1 error. If you're acquitting a guilty man, this person has done something wrong, but you're saying no crime has been committed. So this is a type 2 error. Depending on your beliefs, one of these two types of errors might be more serious. In the case of medicine, we can see that you have to weigh these two types of errors very carefully. If you have a type 2 error and you're saying you are not sick, you don't need any treatment, when the person is actually sick, there might be very severe consequences and this person might die. So they're more likely to make an error where they say you might have a specific sickness, we're not completely sure, and then follow-up research will confirm this in more extensive tests. So Nyman himself says that determining how the balance must be struck should be left to the investigator. So it's up to you to decide what types of errors or what levels of errors you find acceptable. You don't really need to use these defaults, although they're very tempting. Cohen himself recommended this 80% power threshold. And when he did this, he explicitly hoped that this recommendation would be ignored whenever you as a researcher can make better informed judgments. At our department, for example, we use typically a 90% power if we're designing new studies where we hope that they will lead to insights that we can publish. So we have a 90% threshold because we try to spend the tax money on research that will give us informative results. Even when we don't find a significant result, we want to be reasonably sure that there's really nothing there, that we didn't miss anything. In the case where you're examining very impactful things, where if you find an effect, you might have a real breakthrough. So missing out on a true effect is very costly. You want to increase your power or reduce your type 2 error as much as possible. Most of the scientific discoveries that lead to Nobel Prizes are discovered by people between 35 and 40 years of age. So in my case, I'm of course keeping my type 2 error rate as small as possible, because at this moment when I do a discovery and I miss out on something, I could maybe even be missing out on my Nobel Prize winning idea. So for me personally, I try to have high power and low type 2 error rates. The type 1 error rate is slightly less important. At the same time, we see that people are very, very hesitant to change type 1 error rates. You could even increase it. You could set your type 1 error rate to 10%, and it's perfectly possible if in your specific situation this is acceptable. But it's almost like Moses came down from Mount Sinai and he had these tablets with the 10 commandments, and one of them was, you will always set your alpha to 0.05. People are very hesitant to change this, but if you really know what you're doing and you're making an informed judgment, this is perfectly possible. So it's very useful to think about how you can control your error rates when you're designing a new study. You want to minimize one or both of these types of errors, so that in the long run you won't make a fool out of yourself too often. So here we are with Zoltan Dines, the author of this book, Understanding Psychology as a Science. So it's really nice that you want to be here.
Nice to be here.
Take some time for this conference that we're at. Take some time for this interview. So first of all, I was wondering, how did you get into this topic? What decided that you would write about things like this or find them interesting?
My interest goes back quite a way, actually. My mother was a Scientologist, and the headmaster at the sixth form I was in gave me a book on Popper. So I read about Karl Popper, and he discusses what makes something a science and not a science, and that had a pretty big impact on me and how I viewed various movements that might call themselves a science or not. The fact that also it's not just a label, but Popper wanted to point out that how you approach that really matters to the quality of the knowledge that you get.
Okay. I see that you have some interest. One of the examples comes from precognition research and psi research. And you did some studies about yourself, right?
Yes. Now there's a topic where the sort of philosophy of science, philosophy of statistics really comes up. So if you investigate a topic where a lot of people think the hypothesis, the theory, has a very low prior probability, then just using p-values, saying p less than 0.05, somehow doesn't seem right. And then to make a binary decision at the end of that doesn't seem right. Whereas saying there's a certain amount of evidence here, and that will change your opinion by a certain amount, just seemed a better way of dealing with theories where people might have radically different views about them in the first place. So that was in fact my first application of Bayesian statistics.
All right. When you were doing that research, that's when you ventured into this direction of Bayesian statistics.
Yeah, initially, 1980s, I was doing my PhD at Oxford, and Oxford invited this statistician from UCL, John Keir, who had been Piaget's statistician and Hans Eysenck's statistician, and he came to teach the PhD students at Oxford every Wednesday afternoon, statistics. I found him quite captivating, charismatic, but he would teach just whatever he wanted to teach, and one term he said, I'm going to teach you Bayes. And by the end of the term, there's just me and one other person sitting there, and I found it absolutely fascinating. But the other people just thought, "Oh, this is not relevant to my thesis," all disappeared.
All right.
So my little Bayesian Bayes factor calculator actually programmed up at that point, way back then, in late 1980s.
So that's actually an interesting point, right? So you say that most of these students slowly left, but now, of course, if you write this book, there's a lot of topics in here that have to do with Bayesian statistics and likelihood. So apparently you thought it was worthwhile that these students shouldn't leave. Actually, you thought it was worthwhile to explain more students about this. So why do you think it's important that students learn about these topics?
It's important because there's a debate about how one should do statistics that isn't settled, or it seemed to be settled, but it wasn't. And the way we had settled on doing things caused problems. That's why I had the credibility crisis. That was a big part of it. And now people are really thinking about how should we do statistics, how should we do science. And I think in 10 years' time, results sections are going to look rather different than they do now. And you can either be ahead of the curve on that, or you can be desperately trying to catch up later. And the people we need to reach are the current students coming up. They need to understand these issues, and where researchers have gone wrong in the past that led to science that wasn't really that credible in the end. And if you don't understand statistics and the philosophy of science more generally, then you'll make the same mistakes again. So I think this is the time to change. Change is happening. 10 years time, science will look very different. I actually think in 100 years time, people will look back on how we do science now, and it'll be a bit like how we look back 100 years ago. And you say, really, they did like that? That's pretty primitive. And a lot of the changes that will be coming about and affecting how we do science in the future, they're happening right now.
All right.
So it's quite exciting in a way.
Yeah, I agree. Okay, very good. So when you were examining all these things for yourself, these statistical techniques and figuring out, mainly this was because you need to analyze your own data, right? I mean, you're not, in principle, a statistician yourself, right?
No, trained as a psychologist. Exactly.
So you're trying to figure out how to use this. So what things were most helpful to you, or most insightful or eye-opening when you were learning about these things?
I think when I wrote the book, and I don't know if it comes across there, but probably I was leaning towards a likelihood approach. That's sort of the...
It comes across a little bit, I noticed, a little bit.
Yes. And well, either that or Bayes, for me a big issue was how you deal with non-significant results, because in my field, non-significant results were often used to draw inferences. My field being unconscious knowledge, say unconscious perception, implicit learning, and how you establish that perception is unconscious, subliminal, or learning is implicit, is often by getting a non-significant result. But just getting a non-significant result in itself doesn't have evidential value. So what do you do? Well, so I was looking at likelihood inference and Bayes, and then just through having to really apply them in real situations, not write papers about statistics, but do psychology and apply those techniques. I found Bayes was just the most useful, because typically when you have a theory, you're saying, well, there's a range of possibilities for what the population hypothesis could be. Some are more plausible than others. And that, as soon as you accept that and want to get evidence from another hypothesis, you're led to Bayes factors. And I've just found that enormously helpful. And if you look at how I write papers now, even compared to 3 years ago, it's just radically different. And I look back to how I wrote papers, really just bearing in mind just following through the logic that's contained in that book, but just following it through and actually applying it. Every step of the way has turned around how I do science.
So you'd say you're still learning about these topics yourself? Still
learning, exactly. So since 2008, when the book was published, I've been thinking about how do I actually apply it in real situations. So exactly the same logic that's in there, but putting it into practice is what I've been working on.
All right, great. Thanks so much. In this lecture, we'll talk about likelihoods. Likelihoods are a way to express the relative evidence for one hypothesis over another hypothesis. They can be very useful in themselves, but they are also underlying a lot of Bayesian statistics, as we'll see in later lectures. A likelihood gives you the function of a parameter given the data. So when you've observed some data, you can plot the accompanying likelihood function, and you can check how likely each hypothesis that you might have is. In this example, we'll mainly focus on the binomial likelihood function. This is the easiest situation. It's like flipping a coin and then counting the number of heads that you have observed. This is the binomial likelihood function. I won't explain it in detail here, but there's an accompanying assignment in which we'll dive into the function and calculate some likelihoods for different observations of number of heads. For now, let's take a look at a situation where we flip a coin 10 times. 8 of these 10 times we find that the coin comes up heads. We can calculate the likelihood of theta. And theta in this case is a Greek letter that explains the true hypothesis. And in this case we might assume that the true underlying number of heads that we'll observe if we do this in the long run is 0.8. So for the theta of 0.8 we can calculate that the likelihood is 0.30. But we can also calculate the likelihoods for all sorts of different hypotheses. Let's say that you have the idea that the true value of the number of coin flips in the long run is 70%, or a theta of 0.7. The likelihood for this being true, based on the data that we have observed, 8 out of 10 coin flips turned up heads. The likelihood of the true population effect being 0.7 is 0.23. The likelihood of a theta of 0.6 is 0.12, so you can see it becomes less and less likely the farther away you go from the observed data. Now these numbers are not very clear, so let's take a look at the likelihood function. In this graph you can see the likelihood function plotted. On the vertical dimension of this graph we have plotted the likelihood, and on the horizontal dimension we have plotted theta, all different versions ranging from 0 to 1. So the range of 0 to 1 means that we'll either always observe heads or we'll never observe heads. Now based on the data we have collected, we already know that it's not possible that we'll never observe heads or we'll never observe tails, because 8 out of 10 turned out to be heads. So we've observed both values. So the extremes are not possible, and you can see that the likelihood here is 0. It's very low. The most likely true population parameter of the number of coin flips, based on the data that we have, is 0.8, because this is exactly what we have observed. So this is the maximum likelihood. Based on the data that we have in our hands, we can see that 0.8 is the most likely true population parameter. But some of the values just around it are also still quite plausible. So a value of 0.6 is still quite probable in this case as well. These types of likelihood curves were invented by Ronald Fisher. I already said he was a really smart guy. And he invented these likelihoods when he was only 22 years old and actually a third-year undergraduate student. So this sort of testifies to his genius, I would say. Sometimes I wonder, what have I been doing the last couple of years? Definitely not inventing something like this that's a fundament of modern statistics. Now we can use the likelihood under the null hypothesis and the likelihood under the alternative hypothesis to calculate something that's known as the likelihood ratio. So in the case of the likelihood ratio, we're taking the relative evidence for the one hypothesis, the null, and the other hypothesis, the alternative, and we can calculate the odds of one over the other. Let's look at our example where we had 8 out of 10 coin flips. Now we need to compare two hypotheses, and you're free to choose any two values of theta that you want. But one very logical value would be 50%, 0.5, the hypothesis that this is a perfectly balanced and fair coin. So this is the value that's plotted at 0.5 on the horizontal axis, and you can compare this with any hypothesis you had in advance. The alternative hypothesis I've chosen here is the value 0.8. This happens to be exactly the value that we've observed in the data, 8 out of 10 coin flips. Now we're comparing this alternative hypothesis that the true population parameter is 0.8, so 80% of the time this coin will come up heads, and we'll compare it to the null hypothesis, the value of 0.5, the idea that this is a perfectly balanced fair coin. Now you can already see in the graph that the likelihood is much higher at 0.8 than it is at 0.5, but what we want to know is how much more likely. And the likelihood ratio gives us an idea of this. It's basically dividing the likelihood at 0.8 by the likelihood at 0.5. And in this case, this ratio is 6.87. So it's quite more likely that the true population parameter is 0.8 compared to the idea that the population parameter is 0.5. Now we can test any values that we want. Let's say that in advance we still had the same alternative hypothesis, that this was a coin that would come up heads 80% of the time. We still compare it to the probability that this is a fair coin. So these two hypotheses are being compared, but now we have observed data where the coin comes up heads 4 times out of 10 flips. So we can see the shape of the likelihood function is very different, and in this case, of course, based on the observed data, the likelihood of 0.4 is most likely. We can still compare the ratio of the likelihoods at 0.5 and 0.8, and now we see that the value at 0.5 is much more likely than the value at 0.8. So the hypothesis that this is a fair coin is now much more likely than the hypothesis that this is an unfair coin and that the true population parameter is 0.8. Now when you calculate likelihood ratios, there are two cutoffs of 8 and 32 of these likelihood ratios, which are considered either moderately strong evidence or strong evidence. So in the previous examples, we could see that in the first case, we had not yet moderately strong evidence for the difference in the hypothesis. In the latter case, when we observed 4 out of 10 flips coming up heads, we can see that this was very strong evidence for the fair coin hypothesis compared to the alternative that this was a coin with 0.8 coin flips coming up heads. So you see that likelihoods are relative evidence for the alternative hypothesis compared to the null hypothesis. It's important to realize that both of these hypotheses might be quite unlikely. Let's look at an example. Now here we flipped a coin 100 times, and 50 out of the 100 times the coin came up heads. Now we are comparing two hypotheses here. The one being that the true population parameter is 30% heads in the long run, so a theta of 0.3. The alternative hypothesis is that the true population parameter is theta of 0.8, so we'll see 80% heads in the long run. When we compare these two hypotheses against each other, we can see that the hypothesis that the true population parameter is 0.3 is massively more likely than the likelihood that the true population parameter is 0.8. And we find a ridiculously high likelihood ratio. However, we can also see that both these hypotheses are wrong. So even though the relative evidence for the one hypothesis compared to the other hypothesis is extremely convincing, we didn't find the true population parameter, which is actually just 0.5 in this case. So it's important to keep in mind that likelihood ratios are relative evidence. Now we can compare the likelihood under the null hypothesis of a theta of 0.05 and an alternative hypothesis of 0.8. Now one way in which you can think about applying these likelihood ratios is when you think about the outcomes of studies. Now if you perform a study, it's sort of like a coin flip. You can either find a statistically significant result or not. So this is one of two options, and it's a binomial probability. So how often will you find a significant result and how often will you find a non-significant result? Well, it depends on whether the null hypothesis is true or the alternative hypothesis is true. When the null hypothesis is true, we know that you'll find a significant result that equals your alpha level, which is typically 0.05%. So this is a very good null hypothesis in these likelihood ratios. We can compare this with the probability of finding significant results when there is a true effect. And in this case, this probability depends on the statistical power that you have in your test. Let's for now put it at 0.8. So 80% of the time you'll find a significant result because you had 80% power. Now we can use the likelihood function to compare the probability that we've observed a significant result under the null hypothesis and compare it with the alternative hypothesis. Let's say that we perform 3 studies in a row. Now there are a number of outcomes that could happen, of course. None of these studies could come up significant. You could find only 1 significant effect, or 2, or if you're really lucky, 3 significant results out of 3 studies. Now let's calculate the likelihood of finding 2 out of 3 significant results. When the null hypothesis is true, this is pretty straightforward. The probability of finding a significant effect when there's no true effect is the alpha level, so this is 0.05% of the time. We multiply it by 2 significant studies, so 5% times 5%, and then we multiply it by the probability of finding no significant effect. Well, if we have a 5% alpha level, then the probability of finding no significant effect if there's no true effect is actually 95%. So if we multiply these probabilities, 5% times 5% times 95%, we get the value of 0.0024. All right, So what happens if there is a true effect to be observed? And we find 2 out of 3 significant findings. Now let's assume that we have 80% power. You never really know, but you can check different levels of power in the likelihood function when it's plotted. But for now, let's take a look at 80%. So we find 2 significant results and 1 non-significant result. If the alternative hypothesis is true, this equals an 80% probability of finding a significant result times an 80% probability of finding a significant result times a 20% probability of making a type 2 error. And if we multiply these probabilities, we get 0.128. So we can calculate the relative likelihood of observing this data, 2 out of 3 significant results, when either the null hypothesis is true or the alternative hypothesis is true. Now, based on these numbers, you can already see that this outcome is much more likely when there is a true effect than when there is no true effect. So if we calculate the likelihood ratio, we see that it's actually 54 times more likely that the alternative hypothesis is true than that the null hypothesis is true. It's possible to find this pattern of results when there is no true effect, but it's massively more probable that you'll find this pattern of results when there is a true effect. We can plot this likelihood function, because you might not be convinced that 80% power is very likely in this case. Now, if you look at this graph, we can again see the likelihood function, which is plotted for 2 out of 3 significant results. I've indicated 2 points, the 0.05 theta on the left and the 0.8 theta on the right. Now, the 0.05 is the type 1 error rate, or your alpha, so that's pretty fixed. But maybe you feel like you might have had lower power in your study. And you can look at the relative likelihood of the outcome of 2 out of 3 studies for any value of theta that you like. The most probable situation is, of course, the theta for exactly the result that we have observed, 2 out of 3 significant results, meaning 0.666. For any of these values, you can see that as long as you assume a decent level of power, something higher than 0.5, it's much more likely that there is a true effect than there is no true effect, even though we only observe 2 out of 3 statistically significant results. Now, this is an important realization that you can get by looking at these likelihood functions. Multiple studies should give mixed results when the alternative hypothesis is true, and even when you have a decent level of power, this will happen quite often. What's the likelihood of finding 3 significant results in a row when you only have 80% power? And I'm saying only, but that's actually a pretty decent and recommended level of power, right? So we can do the math. It's quite easy. 0.8 times 0.8 times 0.8 gives you a likelihood of 0.51. So about 50% of the time, when you have 80% power and the alternative hypothesis is true, you'll find 3 significant results in a row. It means that almost 50% of the time you will get some version of mixed results, either 2 out of 3, 1 out of 3, or if you're unlucky, even 0 out of 3, even though there might be a true effect. Now, this won't happen so often, but all these outcomes are probable, and the probability of mixed result is almost 50% of the time. So this is important to realize. When you're doing lines of research, you will not find consistently significant results in all your studies, and this is perfectly fine. This is exactly what you should expect. Now, in this graph, I've plotted a lot of lines that are relevant for a situation where we perform 4 studies. When we perform 4 studies, we can either observe 0 significant results, or 1, or 2, or 3, or 4. So each of these curves plots one of these likelihood functions given the data that we've observed. Now, what I want to point out here is again the massive probability of finding mixed results. And we can see this for all the curves, for 1, 2, 3, or 4 out of 4 results, where the likelihood is highest for mixed results. And that's actually this area. So when we perform 4 studies, and the theta, which means the power that we have, is somewhere between 0.2 and 0.8, so between 20% power and 80% power, then finding mixed results is actually the most probable outcome of a line of 4 studies. Now, we've seen that likelihood ratios allow you to express the relative evidence for the null hypothesis compared to the alternative hypothesis. And this can be very useful in itself. For example, we applied this to the probability of finding significant or non-significant results in a set of studies. And we've seen that it's actually quite likely that you'll observe a mix of significant and non-significant results, even when the alternative hypothesis is true. Likelihoods also underlie Bayesian statistics. So knowing likelihoods is also a good stepping stone to move on to Bayesian statistics, which we'll do in future lectures. In this lecture, we'll talk about Bayesian statistics. In a previous lecture, we talked about likelihoods and expressing relative evidence for one hypothesis compared to an alternative hypothesis. And we've used evidence in this sense just based on the data that we have at hand. But we'll see that very often you have some prior belief that you might want to incorporate with the evidence, and Bayesian statistics allows you to do this. Now let's say that you flip a coin 3 times. The coin comes up heads every single time. Now, do you think that this is a fair coin or not? The data that you have at hand shows that this coin came up heads 3 times. So if you would be a newborn baby, then you don't have any prior beliefs, and all you have is the data that you just observed. So for a newborn, well, a newborn would say it comes up heads every single time. This is just what this coin does. But you have prior beliefs that most coins are fair. You might think, well, this happens. 3 heads in a row, that's a perfectly likely observation. I'm not changing my prior beliefs that this is a fair coin yet. You would want to see more evidence. Now, combining your prior belief with the data is possible in this Bayesian sense. It's not possible when you just calculate p-values. Remember that a p-value expresses the probability of the data, or more extreme data, assuming that the null hypothesis is true. And some people say, this is actually not what you want to know. What you want to know is the probability that the null hypothesis is true, given some data that you have collected. And this is a posterior probability. Given that you've collected some data, and maybe some prior beliefs that you have, what is now the probability that the null hypothesis or the alternative hypothesis is true? So Bayesian statistics allows you to express this probability. It works quite straightforward. You have some prior belief, you have some data, and you combine these into a posterior belief. We can calculate posterior odds that the alternative hypothesis is true, given the data, compared to the probability that the null hypothesis is true, given the data. This is a very useful way to split apart these different aspects of the formula. So the posterior equals the likelihood ratio times the prior. So here you see that this likelihood ratio that we discussed in the previous lecture is an essential part of the probability calculations in Bayesian statistics. But it's also combined with this prior. So how can we do this? We have to come up with a prior distribution. In the case of binomial probabilities, a beta distribution is used. The beta prior is determined by 2 parameters, which are referred to as alpha and beta. Now this can get a little bit confusing because we already talked about alphas and betas as type 1 errors and type 2 errors. Regrettably, we see that statisticians are not very creative when it comes to thinking up Greek letters that they want to use for their statistics. So there are some double use in the literature, and this is one of these examples. A beta prior is determined by alpha and beta. These are just 2 numbers that have nothing to do with error rates whatsoever. Let's take a look at different versions of prior distributions. If we set the alpha and the beta in the beta probability to 1, we see that we get a perfectly flat line. This means that every value of theta, which is plotted on the horizontal axis, is equally likely. So we don't have any expectations, and we say anything that might happen is possible. Now in the case of a coin flip, you might not be convinced that this is what's most likely. In the case of flipping a coin, you can have a lot of different beliefs. One of them is the belief that this is a coin that always comes up heads. If you have a very strong belief that this is the case, then this is your prior. You think that it will be heads almost always, although you're willing to give at least some probability of different values. You might also think that this is a perfectly fair coin. Most coins are fair after all. So you think that this coin should come up heads 50% of the time. You have a very strong belief in this. And it's illustrated in this graph where there's a very high peak at 0.5 on the theta. But you're also willing to allow for some variation. It might be that the coin is not perfectly fair. It might have been used and it might be an old coin. It might come up heads a little bit more often or a little less often. Now let's combine our prior belief, whatever it is, with the data that we've observed. So we have a beta prior distribution and we have the likelihood function, and we can quite easily combine these into a posterior distribution. The posterior is also a beta distribution with an alpha and a beta value. And the alpha and the beta are determined simply by adding the alpha of the prior to the alpha of the likelihood function minus 1. The same is true for the beta. The beta of the prior distribution added to the beta of the likelihood distribution minus 1. Let's see how this works. In this case, we have a prior distribution that's uninformative. Anything goes. So this is the prior before we collect some data. And now we collect some data and we have a likelihood function. In this case, we flip the coin 10 times. 6 out of the 10 times we observed heads. So that's expressed by this likelihood function. And now we will combine these two functions into a posterior distribution. You now see a black line that falls exactly on top of the likelihood function. This is what meant with an uninformative prior. Everything was equally likely beforehand, and it doesn't influence our judgment in any way. We just believe whatever we have observed, exactly the same. So the prior does not influence the posterior distribution in any way. Let's take another example where this is the case, where the prior does influence the posterior distribution. Here we have some belief that the coin is probably fair. We think that values around 0.5 are somewhat more likely, but we don't have a very strong conviction about this. We again observe the same data. We flip the coin 10 times and 6 out of 10 the coin lands heads. So this is exactly the same likelihood function that we had in the previous example, but we have a slightly different prior. Combining our prior belief with the observed data yields a posterior distribution that no longer falls exactly on top of the likelihood function. Indeed, we see that the posterior is slightly shrinking towards the prior belief that we hold. Now, using the prior distribution and the posterior distribution, we can calculate something that's known as a base factor. The base factor is the relative evidence for one model compared to another model. Now compare this to likelihood ratios. In a likelihood ratio, we only have one distribution, and we're comparing two different values of theta on the likelihood function. But here we'll use the likelihood from the prior distribution and compare it to the likelihood of the posterior distribution. Let's take a look. We have data from 20 coin flips. They came up heads 10 times. Let's take a look at two different priors. Either a beta prior of 1 and 1, which means it's completely uninformative, the uniform prior. But we can also compare it to a beta of 4, 4, where we have some expectation that this is a fair coin. Now in this graph again, we see the prior distribution in the gray line. That's uniformly distributed. We don't have very strong prior beliefs in this case. Everything is equally likely. Then we've collected some data, and now we have a posterior distribution, which in this case falls exactly on top of the likelihood function. You can see that there's a relative difference of the likelihood of both of these functions at specific points. Now we have to pick one hypothesis that we're interested in. Let's say that we want to know whether this is a fair coin or not. So in this case, we would test the hypothesis that theta is 0.5. We can compare the prior distribution with the posterior distribution to see how much our belief has changed by collecting some data. So the prior at 0.5 was much lower than the posterior is at 0.5, and the ratio of these 2 points is 3.7. This is a slightly different version where we only have a different prior. We've observed exactly the same data, but the prior now was slightly more informed. We already expected that this coin would be fair. We collect the same amount of data, and we again see that for the theta of 0.5, the hypothesis that this is a fair coin, our belief in the hypothesis that the coin is fair has increased. But because we already had quite a strong prior, the data only increases our belief with 1.9. So after looking at the data, the hypothesis that the theta is 0.5 has become either 1.91 or 3.70 times more likely, depending on the prior that we had. So we can see how Bayes factors tell you something about the increased evidence or the belief that you have about a specific hypothesis, compared to your prior and the posterior. Now we can also look at Bayesian statistics not from an hypothesis testing viewpoint, where you test the hypothesis and the prior and the posterior, but we just want to estimate which values do we think is most likely. So this is not Bayesian hypothesis testing, but it's Bayesian estimation. We also use the posterior distribution to estimate. So instead of testing two different models, the prior and the posterior, we will use the posterior just to estimate plausible values. Which values do you believe are most likely, based on your prior belief and the data you have observed? In this graph, we again see a prior distribution and a posterior distribution. And in this case, because we have an uninformative prior, the likelihood and the posterior fall exactly on top of each other. We can calculate the mean of the posterior distribution, and we can calculate what in Bayesian statistics is known as a 95% credible interval. A credible interval contains 95% of the values that you find most plausible. So this is an expression of your belief. Which values do you believe are most likely given your prior and the observed data? Now in this case, because we have used an uninformative prior, you can see that the likelihood function is basically everything that matters. The posterior distribution is completely determined by the data. And this is a situation where the 95% credible interval in Bayesian statistics exactly matches with the 95% confidence interval in frequentist statistics. But that's not always the case. This is only true when we use an uninformative prior. Let's see how this changes when we use a more informed prior. Now let's take a look at a slightly different situation. A rather extreme example where we had a very strong prior belief that the coin would come up heads about 2/3 of the time, so 0.666. You can see the gray distribution peaking at this point. So this was our prior belief before we collected some data. But then we collect data and we actually find a completely different pattern. We see that the coin came up heads about 40% of the time. And we collected quite a lot of data. So the blue likelihood function is completely different. We can also see that the black posterior distribution is now a little bit in between of both of these functions. So the data and the prior are merged into a posterior distribution. And the 95% credible interval now contains values that no longer match with the 95% confidence interval. Our very strong prior has made it so that our belief in the most likely, most plausible values, the values that we feel most confident in, are no longer exactly matching up with the data, but they're slightly influenced by the prior that we have. This also shows a strength of Bayesian statistics. We had a prior belief, which we quantified by putting a function on it, and then we observe some data, and we can see that our belief can be changed. In this case, our posterior belief is still sort of halfway in between, but if we collect enough data, we should see that the posterior belief becomes very, very close to the likelihood function. So this shows that if we collect enough data, then we slowly update our belief. We can become convinced about something else. This is, of course, a very useful way to do science. And this is also the difference between science and religion. In religion, you would not have any option to update your belief. But in Bayesian statistics, we have a very logical framework where data can change our prior beliefs and lead to new posterior beliefs. So this 95% credible interval contains the values that you find most plausible. It's all about expressing and quantifying your belief in specific values. Now in this lecture we've seen how you can use Bayesian statistics to quantify your prior beliefs, collect data and then update your beliefs based on the data that you have observed. Now, in the previous lecture, we talked about Bayesian statistics, formally quantifying your prior belief, updating it based on data into a posterior belief. There's some debate in the literature about whether people should always use Bayesian statistics or not. It depends on how happy you are with incorporating mainly subjective prior information into your statistical reasoning. Here I want to talk a little bit about how it's important to at least use Bayesian statistics some of the time, even if you don't want to formally quantify it, to think about statistical inferences. So even if you don't want to quantify your inferences using a subjective prior, it's always good to keep prior information into account in some way. Now, taking prior probabilities into account is very often smart thinking. We can look at an example from medical science to see the point of thinking about priors. Now, let's take a situation where about 3% of the people in the population is sick. We have a test that can identify whether you have this illness or not, and this is correct 80% of the time. So this equals a statistical power of 80%. In 80% of the cases where you are sick, the test will tell you that you're actually sick. Of course, we also have a type 1 error rate, and we've seen that in medical science, this is often a little bit higher just to be sure. Better safe than sorry. So in this example, there's a 13% false positive rate, or 13% of the people who don't have this illness will be identified by the test as maybe being sick. If you get the test and there's a positive result, and remember, positive result in a test in medicine is not very positive. It means that you've been identified as you might have an illness. Given a positive test result, how probable is it that a patient is actually sick? Now let's visualize this by looking at a large population of individuals. And in this population we see that about 3% of the individuals, the red ones in the corner, are actually sick. They actually have this illness. And it means that 97% of the people are not sick to begin with. So this is a situation where the prior probability of being sick is actually quite low. And then we collect some data. We perform a test. And in this test, we see that a number of individuals are identified as having a specific sickness. Now, for the people that actually have this sickness, we can see that we had an 80% probability of exactly determining that they had this, right? So the true positive rate, or the statistical power, was 80%, which means that 4 out of these 5 will be correctly identified as being ill. But we also had this large false positive probability of 13%. So we see that in this cluster of individuals, there's actually quite a large number of people that are identified as maybe being ill based on a type 1 error. So given that this is the data that we have observed, what is now the probability of actually being ill? And we can see that this is just the probability of being one of the red individuals divided by the probability of one of the black individuals. We can also formally quantify this again as we did the previous time. We have the prior times the likelihood, which equals the posterior distribution. In this case, it means that before we started, we actually have 175 people here on this slide. 5 of them were actually ill to begin with, and 170 weren't ill. Then we have the data. 4 out of 5 were correctly identified as being sick, and 22 out of 170 were identified as maybe being sick, but these were all false positives. And if we combine this and then calculate the posterior probability, we actually see that it's based on the outcome of the test now only 18% likely that you're actually ill. So this probability is surprisingly low, and we see that many medical doctors overestimate the probability that someone is really sick if the frequency of this illness is very low in the population. So at least some implicit Bayesian statistics is useful, realizing that if something is pretty rare to begin with, a positive test result might not tell you so much yet, and follow-up tests are definitely required. So taking prior information into account can lead to better inferences. I'll show you a very intuitive way to do this when you're thinking about p-values, and when you're using p-values to more or less update your belief. Now, p-values were not meant to do this, but there are some statistics that point out an easy approach to give you the most likely posterior probability of the hypothesis being true given a p-value. And again, this is not formal Bayesian statistics, but it's a very easy way to at least use a little bit of Bayesian thinking. Now this is known as a nomogram, this graph that we have, and there are 3 vertical lines, one on the left, one in the middle, and one on the right. This type of graph is very often used in medical institutions where, for example, nurses cannot be expected to perform formal Bayesian statistics on the fly when they see someone cough and want to think about the probability that this person is either just having the flu or having Ebola. But using a graph like this can very easily give you some indication of the posterior probability of an hypothesis given a prior probability and an observed test result. Now in this graph on the left we see the prior probability that the null hypothesis is true. In the middle graph we see the p-value that we've observed, and on the right we can get the posterior probability that the null hypothesis is true. Now let's start by thinking of a situation where we, before we collect some data, think that anything goes. So a person might be sick or not, and both of these are 50% probable. So here I've pointed an arrow at the 50% prior probability that the null hypothesis is true. We collect some data, and then let's try to quickly use this graph to update our belief. In this case, we collected some data and we found a p-value of 0.05. So this is exactly on the border of statistical significance. We got lucky, it's just exactly statistically significant. But as many people who practice Bayesian statistics will tell you, such a high p-value, relatively high, even though it's statistically significant, is actually not a lot of evidence. And this graph nicely illustrates this. If you had a 50% prior belief that the null hypothesis is true, you collected some data, then on the right, the point where the line hits the vertical axis is actually at about 29% posterior probability that the null hypothesis is true. So we started out with a prior belief that it was 50% likely that the null hypothesis is true. We observe some data and we find a barely statistically significant p-value. And then of course it makes sense that our prior belief that the null hypothesis is true is a little bit lower. But you see that it's not a lot lower. It's actually still 29% likely that the null hypothesis is true, even though we've observed a p-value of 0.05. Now this is one of these ways in which you can use Bayesian thinking to at least acknowledge that a relatively high p-value doesn't mean that the null hypothesis is now completely unlikely. Let's say that you had the same prior belief, but you observed a much lower p-value of 0.001. In this case, we can see that the point where this line hits the right axis is around 2%. So given this quite strong data, we now have a prior belief that the null hypothesis is true of only 2%. So that's a huge drop. We started out with a 50% prior belief that the null hypothesis might be true. We collect data and now we think it's only 2% likely that the null hypothesis is true. So we've learned quite a lot. Now you can also use this graph in a very interesting way to think, okay, so what about hypotheses that a priori, before I collected some data, I found really unlikely to be true? Now it's always a bit tricky because we're talking about subjective belief. So what is an unlikely hypothesis? At least sometimes people in the literature will identify surprising results themselves. They say, we published this result and this is a very surprising finding. So that means that before they started, it was at least less likely to be true than that it was likely to be true, right? We're not at 50-50, but the prior probability that the null hypothesis is true was somewhat higher. Let's put this prior belief at about 75%, right? Sounds about fair. So we have a 75% probability that the null hypothesis is true before we start. We're slightly skeptical that something is going on. We again collect some data and we find a p-value of 0.05. Then the line continues on to the axis on the right, and again this gives us the minimum posterior probability that the null hypothesis is true. And you see, because we started with 75% prior probability that the null hypothesis is true, we observe a just significant result. But after this, it's actually still more likely that the null hypothesis is true than that the alternative hypothesis is true. So this is an interesting observation, even though we observe a statistically significant result, because beforehand this result was actually very, very unlikely to be true. After collecting the data, we are still not convinced. So this is an easy way, without very formal Bayesian statistics, to at least give you a rough estimate of the best case scenario for the null hypothesis, which might actually not be very good based on very high p-values. This is in line with a claim by Laplace, who says that extraordinary claims require extraordinary evidence. So very high p-values in a situation where we think that the hypothesis is extremely unlikely. Think about things like precognition. Do you think that precognition is true or not? Well, you might have some belief that it is possible, but you don't think that it's extremely likely to be true. Otherwise, we would have seen some evidence for it by now. So your prior belief that precognition is real is pretty low, or in other words, your prior belief that the null hypothesis, that there is no precognition, this null hypothesis, the belief is very high. So if you want to show that there's indeed something like precognition, then you need to provide extraordinary evidence, extremely compelling data that will lead you to slowly update your belief. Now in this lecture I've talked about how you can use Bayesian thinking, even when you don't want to use formal Bayesian statistics when you report your results. You prefer to use frequentist statistics, for example, and you don't want to quantify your prior belief and update it based on the data into a posterior belief. It still makes sense to use a little bit of Bayesian thinking, to keep in mind how likely the hypothesis was before the data was collected, and weigh the evidence in relation to the extraordinariness of the claim. In this lecture, we'll revisit type 1 errors, and we'll take a closer look at one problematic aspect of type 1 error control, where we see that in the scientific literature, people are sometimes inflating their error rates by certain practices that lead them to conclude that there is an effect when there's actually no effect, at a much higher percentage than the alpha level that they've decided upon. And it's important to not make this mistake yourself. So just to revisit, the type 1 error is the situation where you say that there is something when there's actually nothing that's going on. So you're concluding that there is a true effect when the null hypothesis is actually true. So typically we set an alpha level at 0.05%, which means that in 5% of the studies we do in the long run, where the null hypothesis is true, we will say that there is an effect to be observed, but we'll be wrong. So this is a choice. You can set this alpha level at any level that you want, and in physics it's very typical to use the 5 sigma level, which is this very, very low alpha value that you see below. Now, one problematic aspect that inflates the type 1 error rate, so that increases the number of times that you will say that there is an effect when there's actually nothing going on, is when you make multiple comparisons. So you collect some data, and you do one test, and another test, and another test. So this is a multiple testing situation. And if you do this, the probability of saying that something is going on somewhere inflates well beyond the 5% level. Let's look at a situation where we perform an ANOVA, and this is a 2 by 2 by 2 ANOVA. So we have 2 factors times 2 factors times 2 factors. In this situation, you actually have 3 main effects that you can test for, 3 two-way interactions, and 1 three-way interactions, which totals to 7 tests that you could perform just based on this one study that you've done. In this case, the type 1 error rate, if you do all these tests and you say, well, look, something happened over here, let's interpret this, is actually much higher than 5%. You can see that the type 1 error rate of stating that there is something in one of these 7 tests is 1 minus 0.95 to the power of 7. In total, this is actually a 30% error rate. So you see this is quite substantial. The probability of saying there's something when there's nothing is much higher than the 5%. So this is one situation where you have to think more clearly about what you're doing and what you're testing to make sure that you control the type 1 error rate and to prevent it from being inflated. Now this is a graph where you can see the probability of a type 1 error given the amount of tests that you do. And you can see that there's a steep line here. It's really increasing. The number of tests that you do, the more of them, the higher the probability that you'll say that there's something when there's nothing. And with about 60 tests or something, you have a really almost always something will turn out to be statistically significant just due to random variation. This is the example that we looked at before. This is the 2 by 2 by 2 ANOVA, where we have 7 tests and we test everything. Now in this graph you can see the vertical line, the graph on the side that's saying the type 1 error rate. So all the p-values smaller than 0.05. And you can see that this should be at the level of the horizontal line. So the horizontal line is the type 1 error rate that you should expect in this situation. But you see that the actual observed type 1 error rate is much, much higher because we are doing many, many different tests. You can control this type 1 error rate, and you can do this if you design your study well and you change the alpha level based on some considerations. So how can you do this? How can you control the type 1 error rate to prevent this inflation? The most common way that you can do this, the easiest way, is the Bonferroni correction. It's called the Bonferroni correction, but a better name might be the Dunn collection. So this is Professor Dunn who actually came up with this idea, and when she did, she said, well, I cannot find anything in the scientific literature that uses this before, and it might be so simple that people just didn't think about it. So that's one of the strengths of this Bonferroni correction. It's so remarkably simple to control your error rates that, well, until it was discovered by Professor Dunn, nobody had actually come up with it. But it's very easy to do. In this case, the alpha level that you'll use isn't 0.05 or whatever you set it to for a single test. It's the alpha level divided by the number of tests that you do. So let's say you do 2 tests. You'll divide the 0.05, your overall alpha level, by 2 and have a 0.025 alpha level for each individual test. In the case of the ANOVA, you will actually divide your alpha level by 7, for example. Alternatively, you can multiply the p-value by the number of tests, and it's exactly the same, and then you use the 0.05 alpha level for each specific test. If we take this latter approach and we plot the p-value distribution when we have applied a Bonferroni correction to the same situation we had before, you see this very peculiar distribution of p-values. In this case, you see that the alpha level is exactly controlled. You see in the bottom left there's this type 1 error rate, which is actually at 5% of the total number of simulations in this case. Due to the multiplication of the p-values, we see that there's a bar on the right side of this graph that's completely going through the roof. Most of the p-values are actually here. So we multiplied all these p-values and a lot of them become really, really high, or actually 1. But at least the number of times that we'll say that there is something when there's nothing is nicely controlled in this situation. We have to control not just the single test that we do, but what's known as the family-wise error rate. You have to control for all tests that will lead you to say that there is something when there is nothing. In the situation where you have 7 tests, and you will take any test as an indication that something is going on, well, the family in this case is 7 tests. But you could also say, well, arguably, I didn't do a 2 by 2 by 2 ANOVA because I was interested in main effects. You're typically interested in an interaction somewhere, maybe a 2-way interaction or a 3-way interaction. So in this case you would say, well, there are actually only 4 tests that I'm really interested in. This is my family, and therefore I'll divide my alpha level by these 4 tests. Now sometimes you have a very specific prediction and you don't really need to use a Bonferroni correction. If there's only one thing you're interested in, like Research Wahlberg says here, if you are only interested in one girl, there's no comparison. If you're only interested in one statistical test, then you don't need to adjust your alpha level. If you're saying, I'm actually only interested in the 3-way interaction, then that's the only test you'll do, the only situation where you'll say, this indeed supports my hypothesis, and you don't need to control your alpha level any further. In these situations, it makes sense to write down your prediction before you do it. And later on, we'll talk about pre-registration as a way to control error rates and write down what the alpha level is and the test that you want to do. It turns out that the Bonferroni correction is slightly conservative. You can do a little bit better. In practice, it won't matter so often, but given that we use computational tools to calculate these corrections most of the time, why not use the slightly more efficient version? This is called home correction, In this case, you order your p-values, you inverse the rank order, and you say which is the lowest p-value and the second lowest and the third lowest. And you multiply the p-value by the inverse rank order to get a corrected p-value. So you see that for the lowest p-value in this situation where we do 4 tests, we actually multiply this very low p-value by 4. For the second lowest, we multiply it by 3, etc. The benefit is clear in the last line here, where we have the 0.032, the p-value that we've observed, but this is the last that we want to test. In this case, the inversed rank order is 1, so actually we don't have to correct for it anymore. So this is the p-value we can interpret at a 0.05 level. In this case, this can be considered statistically significant, whereas if we would use a Bonferroni correction, this would no longer be statistically significant. Now this is a graph visualizing the Holmes corrected p-value distribution. And you can see it's slightly different than the Bonferroni correction, but again the p-values are 5% of the time they fall under the 0.05 level, and the type 1 error rate is adequately controlled. So we talked about multiple testing, and this is one situation where you can inflate your alpha level. Another widely used problematic research practice is known as optional stopping. In this case, you collect some data, you analyze the data, and you do the statistical test, and you see whether the data is statistically significant or not. Let's say you're interested in whether the p-value is smaller than 0.05. If this is not the case, you collect more people. You have additional observations. This is quite common practice in many research areas. And it sounds like it's a good idea, right? It sounds like you should want to do this because it's a very efficient way to collect data. If you look at the data and it's already statistically significant, what's the use of continuing on? Regrettably, if you don't control your error rates in this situation, this actually inflates the type 1 error rate. So even though this is something that you might want to do, you can do it, but you have to do it the right way by controlling the type 1 error rates in this situation. Let's take a look at how you can do this. Now first, let's take a closer look at the problematic aspect of it. If you do this often enough, then formally, using this approach will always lead to a statistically significant result. Alright, sometimes you have to look at the data 100,000 times, so it might not be very practical, but formally, as long as you continue looking at your data and nothing is going on, you will have a 100% success rate. So in terms of good research practices, I would not recommend it, but it is a practice that will give you a guaranteed result 100% of the time. Now obviously it will hugely inflate your error rate, so that's not what we want to do. Let's take a look at how we can do this the correct way. In this graph we see the distribution of p-values when we're using optional stopping. In this simulation we've looked at the data 5 times. There's no true effect, so we should observe the uniform p-value distribution, but you can see there's this very weird peak on the left side of the graph, and there are way more p-values statistically significant than there should be. We have, by looking at the data repeatedly, sort of scratched away some of the nearly significant p-values and pulled them just below the significant threshold. What we can do is use a technique that's called sequential analysis. In sequential analysis, you can look at the data repeatedly while controlling your type 1 error rate. You're using something that's very similar to a Bonferroni correction, but it's actually even more efficient. In principle, you could just use a Bonferroni correction. You can just decide how often you want to look at the data, let's say 4 times, and then divide the alpha level by 4. That would be perfectly fine. But the sequential analysis approach is slightly more flexible and more efficient. Now you don't have to read this, the font is too small to be read by you, but I'll explain what's going on. This is a quote from a paper by Wald in 1945, where he introduces the sequential ratio probability test. This is a new statistical tool at this moment, and when he was examining it was 1943. This was during the Second World War. He had done the math and said this is actually a very efficient way to collect data. And they wanted to use this in the war effort to test, for example, ammunition. Every now and then they had to do a test. Is this working correctly or not? And using this sequential approach made them much more efficient, which is why the National Defense Committee said, we cannot share this knowledge at this moment because if you would publish this in the scientific literature, our enemies, in this case the Germans and the Japanese, would also discover this technique and use it and become much more efficient. So this is the explanation about Walt saying that he only published it in 1945 after the war because this was deemed such an efficient technique that the US government said you cannot share it with the enemy during wartime. Now this is interesting, right? So there is this technique that correctly controls error rates and that will make you much more efficient. But at the same time, we're not using it very often. There are many researchers slightly hesitant to new statistical approaches, but my prediction is that this will be used more and more in the future just because it's a very efficient way to collect data while controlling error rates. If you want to set an alpha level using this sequential approach, you can do so in many different ways. The easiest that I will give an example for in the next slide is that you lower your alpha level to the same level for each time that you look at the data. But as I said, there's much more flexibility that's possible here. You can spend your alpha level over each look at the data in any way you like. You can only have a very, very strict alpha level at the beginning. Don't spend too much of your alpha level and then later on use most of it when you have the largest sample size. But you can also spread it out evenly over every look, depending on what you want. The easiest way is using a Pocock boundary. This is very similar to just dividing the number of looks by the alpha level by the number of looks. It's slightly more efficient, which is why if you look twice, you have a slightly higher threshold than 0.025, which you would have with the Bonferroni correction, but you can see it's pretty close. So these are the thresholds that you would use if you look at the data twice or 3 times or 4 times. Well, something like that is typically sufficient in a study that you do. Remember that this was the optional stopping p-value distribution where the error rate is inflated. So we see way more p-values, just below 0.05 in this case. Now if we use the corrected p-values based on the Pocock stopping rule, the distribution still looks a little bit peculiar, but in this case, the error rate is exactly 0.05. So this is one approach to control errors. We talked about multiple comparisons using Bonferroni approach. You can use sequential tests and control error rates using, for example, the Pocock boundary. There are many different ways in which you can control error rates, and an alternative to this in recent years is not controlling the error rate itself, but the false discovery rate. Now, I just want to point out that this is possible if you're interested in this and you're working in a field where you're doing many different tests, huge number of statistical tests. Then this is a very interesting approach to consider. And this is a paper by Benjamini and Hochberg that you might want to read. I'm not going to go into too much detail, but it's an interesting perspective to learn about if it's relevant for your research question. Now remember that there's nothing special about this 5% threshold. You can increase it, you can decrease it. As I said before, it's up to you to determine how this balance should be struck. If you want to use a more strict error control or a more lenient version, that's perfectly fine. In recent years, we've seen a lot of people worried about the way that people control their type 1 errors. And there's some idea that the error rate in the scientific literature is inflated. In due, this is because people want to use more flexibility in the way that they analyze their data. Looking at the sequential approach is one way in which you can actually have this flexibility, but you can be more efficient in the same time. In other ways, you have to decide very clearly on which specific tests you are interested in. And defining these tests before you collect the data will also make it efficient to control the error rate. In essence, what I'm saying is that whatever you do, if you set an error rate for yourself, it's very important to make sure that it's not inflated. If you let it inflate, you'll fool yourself much more often than you think you're doing. In this lecture, we'll take a closer look at controlling your type 2 error rate. If you design a study and you're going to go through all the effort to collect data, you want to make sure that the probability that you'll find an effect, if it's actually there, is high enough to make the data collection worthwhile. Now remember that the type 2 error is a situation where you're saying that there's nothing when there's actually something to be observed. So you're concluding that there's no support for your hypothesis, whereas if you would have enough statistical power, you would have said that there's actually a true effect. Let's take a look at a classic question that's asked by Tversky and Kahneman, where they find that actually people don't really know what the probability is that a study will yield an informative answer. They ask researchers to think about the following situation. It is known that an effect exists in the population. So we're sampling from a situation where there is a true effect to be observed. Then there's a pilot study where a difference was observed between two groups. You have some statistics, sample size of 22 for example, a mean and a standard deviation. And you have a second group with 23 people, also a mean that's a little bit higher and another standard deviation. Now you've observed the statistically significant effect in this pilot study. The p-value is smaller than 0.05. The question that Tversky and Kahneman asked is, let's say that you set out to repeat this study in exactly the same way, the same sample size and everything. What's now the probability that you'll observe a statistically significant effect? Take a moment to think about it. How would you answer this question? What Tversky and Kahneman found is that most people say that there's a 95% probability that a replication study will again give a statistically significant result. There seems to be some confusion in what a p-value means. Apparently people take it as indicating that it's now 95% probable that there is a true effect and that the following study will also observe this effect. But the correct answer is that you have to perform a power analysis. In this graph we can see different curves that reflect the probability that we'll find a statistically significant effect if there is a true effect. So in other words, the statistical power that we have is a function of the effect size and the sample size. The larger the sample size, the higher the probability that we'll find a statistically significant effect. And the higher the effect size, the more probable it is that we'll find this effect, even with smaller sample sizes. So taking a look at these power graphs before you design a study is a useful way to think of the number of people that you might need when you perform a data collection. Let's have one specific example. For example, you think you might examine an effect with a Cohen's d effect size of 0.5, which is considered a medium effect. Actually, in psychology, if you throw all psychological research in one big pile, the average effect size is around 0.43. So this is a slightly optimistic estimate, but still possible. Now, if you want to achieve 95% power in the study that you want to design, you actually need to collect 100 people in each condition in an independent t-test to achieve this level of 95% power that you want to get. So that's quite a substantial number of observations that you need to have a high probability of concluding that there actually is an effect when there is a true effect. So the type 2 error rate in this case is only 5%, but getting it this low requires a large number of observations. If you design underpowered studies and you don't think of the number of people you need, for example, to have high statistical power, then you're designing studies that have low informational value. If you do not find an effect, it's very difficult to say that you didn't find an effect because there is no true effect, or that you didn't find an effect because you didn't have enough observations to observe a statistically significant finding. If you design a study with high power, and thus with a low type 2 error rate, you can consider these as severe tests. This is a very good test of your hypothesis. If you really have a very high probability of finding an effect, if it's there, so you have a very low type 2 error, and you don't find an effect, well, that's something to make you wonder if there's really an effect or not. So you see that this is a very informational result. If you have very low power, you don't learn a lot. So thinking about how to control your type 2 errors is very important. In this case, we have a p-value distribution of about 95% power, and you see that in this case you have a very severe test. There is a true effect in our simulation. We have 95% power, so most of the time we will find a statistically significant result. It's very rare to find a higher p-value. Most of the time, if there is something there, we will observe it. So this is an example of a severe test situation where if we don't find a result, we should wonder if there's actually something to be observed. So how can you increase your power? There are several ways, and the most attention is being given to increasing your sample size. That's of course a lot of work. It is a very good way to increase power, but it's not the only way. So let's discuss some alternative options. First of all, you can decrease the measurement error. This is a very important way of increasing the statistical power that you have by reducing the variability in your data. You can think about an IQ test. Instead of asking one question and then basing the IQ score on this one item, an IQ test has many items. Using this approach reduces measurement error and makes it easier to find differences between groups if they are really there. A second approach that you can consider is using a within-subject design. This increases the statistical power, especially when the correlation between the two measurements that you take is very high. In psychology, this is very often the case. Think about a reaction time study where you have people respond to certain images or certain stimuli that are either congruent or incongruent, maybe a Stroop test. We know that reaction times within an individual are very strongly correlated. So using a within design in this case increases the statistical power of observing an effect. A third way that you can try is increasing the variability in the response options. This might make it easier to find differences if there's enough variability in the data. And you can think of the number of items in a scale, for example. If you have a scale with only 3 or maybe 5 items, there's not a lot of wiggle room for people to vary on, even if there is a real difference. If you have a large enough scale, let's say 7 items or 9 items, there's more possibility to have varying responses, and it's easier to find differences if they are really there. Final way to consider is using a one-sided test. If you have a directional prediction and you're not interested in effects that go in the opposite direction, then this is a good approach to increase the statistical power without any additional cost. People are not using these one-sided tests as often as they should, but they're a very efficient way to collect high-powered studies. This is a graph illustrating the difference between a one-sided test and a two-sided test if we're examining a Cohen's d of 0.5 in a one-sided t-test. And you can see that with a one-sided test, you need about 26 people, whereas with a two-sided test, you would need about 34 people. So the difference might be small, but if you have smaller effects, it can become quite substantial. And it's just free if you have a directional prediction and you specify this in advance before data collection. Now, there's some discussion in the literature about which type of error is more severe. The type 1 error, where you say that there is something when there's actually nothing, or the type 2 error, when you say that there's nothing when there's actually something. And it depends a little bit on how we organize our science. As long as there are replications of results, then type 1 errors will be identified. If you try to replicate someone else's study, and this was a type 1 error, it's very unlikely that you will find another type 1 error. The probability of doing this will substantially decrease. It's very unlikely. So as long as we replicate each other's work enough, sufficiently, we will identify these type 1 errors. And you might say, well, they won't impact the scientific literature too much. In this case, a type 2 error might be much more severe. If somebody tries out a new idea and there's nothing there, other people might give up on this idea. So a type 2 error might be more severe depending on whether we do enough control and enough checking in the scientific literature to identify the type 1 errors. As you see, it's very important to control your type 2 errors as well. People are very upset about type 1 errors in the literature nowadays, but you can see that it might be even more severe to miss out on a true effect because your study did not have a high enough informational value. You did not connect enough people to conclude that there is an effect when there's actually a true effect. So be sure that when you're designing your study, you evaluate the severity of the type 1 error and the type 2 error, and in certain situations it might be that a type 2 error is much more severe and it deserves your attention. So we're here in the office with Dan Simons. someone you might have heard of, because in many introduction to psychology lectures there's this video of a gorilla walking through a group of people and people don't notice this gorilla. You might have even read this book, and if you haven't, then I'd highly recommend you do, where he describes this type of research. But this is not what I'm going to talk about today, because Dan Simons is also, together with Alex Holcomb and Jennifer Tackett, an editor at Perspectives on Psychological Science, where they have this new article format. So then, there's this new type of research that's published. It's known as a registered replication report.
Yes.
And people do research, but it's a little bit different than a normal journal paper.
Yeah, it's very much different than a normal journal article. So in a normal journal article, people will run their 1 or 2 studies or 3 studies, they'll compile them into a package, and then they'll submit that as a publication. What a registered replication report is designed to do is to estimate the size and robustness and reliability and consistency of an important finding. So what we do is we find a finding that's already been published in the literature, one that has been cited many times or talked about in the media, that is really influential in the field or in the public, and we design a protocol to directly replicate that study. So to do the same thing again. And we take that design, build out the protocol, write out the scripts, and then we put out a call for other labs that want to join in this project. And they each will then replicate the original study using exactly the same protocol. So we have anywhere from 10 to 30 labs conducting the same study in the same way, across a wide range of cultures and across a wide range of subject populations.
Okay.
And what that allows us to do is to say, how consistent is this effect? We basically combine all of the results in a meta-analysis that allows us to say, what's the overall average effect for this original study, and how variable is it across all of these labs?
So it sounds like the article is almost already written with this protocol perspective. There's already a lot of stuff, and then you just go and collect the data.
Essentially, yeah. So when we design this, we have the study already designed. We can, in principle, write the entire manuscript in advance because we know what the theory is, we know what the history is, we know what the methods are.
Okay.
We build out these methods, labs go and conduct the study themselves, and then they report the results in a standardized way.
Okay, so why is it actually important to publish this new type of article?
Well, one of the critical aspects of this sort of registered replication report is it does something that no other kind of article can do. So lots of studies have been published that are then replicated by one lab in a single study, but any one study can't really be definitive. Any one study, unless it's amazingly large, one study is almost never compelling evidence that withstands all possible forms of variability and all sorts of problems of sampling error. So what this approach does is gives you an unbiased estimate of how big the effect is. And we only will do this for studies that have some doubt about how strong the effect is. Not that we expect them to not be there, but there's only been one study, or it hasn't been directly replicated many times, or there are a whole bunch of related studies that use different methods that suggest similar things, but because only positive results tend to get published in the literature, we just don't know how reliable these sorts of effects are. Many of the originals were done with fairly small samples, which means we again don't have a great idea of how consistent and how big these effects are. So that's the broad goal. It does something that no other method can do as robustly. Lots of replications are great, and single replications are really useful. They provide more information. This provides a lot more consistent information using a vetted, sort of evaluated protocol that makes sure we get it right.
And of course it's certain it will appear in print.
Exactly. So the results of every one of these studies are combined regardless of the outcome, and they all get included in the paper, so there's no publication bias. We don't have only the positive results appearing. We have all results from all of the studies and all of the participants in a single paper, and all of the participants are authors on the paper.
So what inspired you to become an editor and to publish this type of article?
So the idea for this sort of article was something that my colleague Alex Holcomb and I talked about many years ago. So in psychology there were a spate of prominent cases of fraud, and that's not really directly relevant here. This replication or failure to replicate a study doesn't have anything to do with fraud. But the combination of those high-profile fraud cases coupled with the failure to replicate some fairly prominent findings in the literature, as well as a bunch of findings appearing in the literature that lots of people would look at them and say, that just can't be. Right? So we saw this as an issue of incentives. There's a really strong incentive to publish new, novel findings, and not as much of an incentive to make sure that these novel findings are robust, or to measure them precisely. Those incentives were lacking in the field, and one of the things we wanted to do was to say, hey, let's take these findings that people are using in their research, that they're using to build theories, that they're using to make public policy. Let's take a look at these findings and say, are they robust? And we really hope they are, but they just hadn't been tested. So it was a need in the field.
Okay, excellent. Thank you very much. In the previous lectures, we've talked about the importance of controlling your type 1 error rate. An increasingly popular way to make sure that people adequately control their type 1 error rates is pre-registration, where you specify what you're going to do before you perform the study, and then after, when you've collected the data, you can just follow this pre-registered plan to make sure that your type 1 error rate is nicely controlled. Let's talk a little bit about why this is important and how you can pre-register and what you need to take care of when you make a pre-registration. Let's first focus on the importance of pre-registration. Why do we need to do this? Now, this is an example where you don't really need to read the fine print here. I'll explain it to you. But this is the first study in an article by Daryl Bem about precognition. And in his experiment, he had 100 participants who performed a sort of reversed priming task. Normally, people have to categorize stimuli by pressing one of two buttons. And this happens, of course, after they've seen the stimulus. But here, this was reversed. So people first made a choice. They pressed one or the other button. And only then did they see the stimulus that they were supposed to respond to. So if they could predict the future, you would expect that they were right more than guessing average. And in this case, we see that there was a situation where a number of different types of stimuli were used. The reported result here, the main result, is their performance on erotic stimuli. But there are a lot of other different types of stimuli that were used where no differences were found. So, for example, although the performance was higher than chance on the erotic stimuli, there were no differences on negative stimuli or romantic stimuli. Now, if you see this sort of makes you wonder, is this really the main prediction that this researcher set out to test? If we look at the p-value, if you do the math and you have a Bonferroni correction, you want to control the type 1 error rate for all the possible combinations, then this would actually not be statistically significant if we would have controlled our error rate for all possible comparisons. So you see that it's very important to specify which tests you're really interested in before you do the analysis, to make sure that other people who read your article are also convinced that your results and your findings are credible. Now here we see that there's a wide range of options of how to analyze your data, ranging from very exploratory analysis. You just look at your data and anything that happens to stand out you consider as an informative result, to a situation where you slightly torture your data. You don't really look at everything that's possible, but you have one hypothesis, but you look at it from this side or from that side, to a situation where research is purely confirmatory. You specify what you want to do, you perform the experiment, and you analyze the data. So this is from a research article by Wagemakers and colleagues where they argue for the necessity of having a purely confirmatory research agenda. We can see examples in the scientific literature for where this would make sense. For example, in a paper about p-curve analysis, a topic we'll come back to later, Simonson and colleagues analyzed a set of studies from the Journal of Personality and Social Psychology, where the researchers reported results only with a covariate. So you can do a covariate analysis, and it might really answer the question that you are asking. But what we also know is that people are sometimes using a covariate as a flexible way to look at their data from a different perspective, with the goal to reduce the level of the p-value. So their initial analysis might not show a statistically significant effect, but then they play around with their data just a little bit until adding a covariate would make a statistical analysis significant. So when they look at a set of studies that use covariates, they see that the P-curve analysis shows that these studies actually lack evidential value. So using this flexibility leads to a set of studies in the scientific literature that really don't tell us anything about what's likely to be true. So recently, people in psychology have been starting to think about how can we change this type of flexibility? How can we make sure that people actually report the analysis that they set out to do in the beginning? And an increasingly popular solution is the use of registered reports, where people write down their predictions before they perform the data collection, and then they analyze their data just by following these reports. Now, it's very important that this specifies the plan of the analysis of the main hypothesis. Of course, it doesn't prevent you from exploring your data. This is perfectly fine, but it just differentiates between pre-registered, confirmatory research and more exploratory research. So in this way, pre-registration formalizes the type 1 error control. You have a very specific plan that you set out to do, and all the tests that you do that follow your pre-registered hypothesis have a controlled type 1 error rate. For other analysis, more exploratory analysis, you can test anything that you'd like, but in this case your error rate is inflated to an unknown level. So you don't really know the probability that you're making a false positive result. Does this matter? Aren't we making life a lot more complicated by asking researchers to pre-register their hypothesis? Well, there are some data to show that there is indeed a benefit of pre-registering and preventing this flexibility. This is from an analysis of a set of studies that were large randomized controlled trials in medicine, either before it was formally required to pre-register your study, the design and the analysis plan in clinicaltrials.gov, and after this was formally required. So on the left we see that from all the big randomized controlled trials, some don't show any statistically significant result, but many actually do. 17 out of 30 studies before 2000 actually show a significant result. After pre-registration became required, this percentage dropped to only 2 out of 25. Now this is an indication that if we ask people to specify their hypothesis beforehand, they don't always succeed in confirming their hypothesis. Which is totally fine, of course. It's very important to realize that your prediction did not hold up. There might have been new insights in exploratory analyses in these studies done after 2000, but these need to be confirmed in follow-up research. So we see that the main goal of pre-registration is distinguishing confirmatory research from exploratory research. This is sometimes called harking, hypothesizing after the results are known. If we think back to the study we described in the beginning about precognition, where a researcher tests all sorts of hypotheses, then after looking at the data, a researcher might think, oh, of course, there's something very special about erotic stimuli that's not present in negative stimuli or in romantic stimuli. And this researcher might come up with a hypothesis of why it's actually very plausible that an effect has occurred. But this is hypothesizing after the results are known. This is creating a hypothesis based on the observed data, and that's reversing the empirical cycle. When you're exploring data, you can perform a hypothesis test, but you can't test a hypothesis. This is a statement by de Groot who already pointed this out in the 1950s. The point here is that it's perfectly fine to explore data and look around patterns that you might find. But when you do this, you cannot test whether this hypothesis is actually true, because what you have done, you have actually tested the hypothesis on the same data set that was used to generate it. The alpha level in this case is unknown, and it is inflated to an unknown extent. So you can never be sure whether this is a type 1 error or not, and you can make no statement about the frequency of type 1 errors in the long run if you are allowing yourself to be so flexible. So when you pre-register your study, what are things that you need to specify? Well, as we've seen, optional stopping is one way in which you can inflate your type 1 error rate. So one thing that you have to do is justify your sample size. Of course, thinking about your sample size before you collect data is also very useful in controlling your type 2 error rate. Thinking about how many people you need will control both these error rates, but it will fix the type 1 error rate to whatever level you've specified. This is sometimes known as the stopping rule. And it can be anything. You can collect data until it starts to rain outside or until the week is over, anything that you want. In a later lecture, we'll talk about justifying your sample sizes. Another thing you need to specify is the independent variable and the dependent variable for each test that you want to do. What is it that you're actually going to analyze? What are the conditions in your study, and what are the dependent variables with which you measure whatever type of effect you predict? For the dependent variable, it might be relevant to say, I'm using a questionnaire and these are the items that I will average, and I will perform my analysis on this averaged score. It matters whether you'll do this or maybe use one of all these items, so this flexibility should be prevented by specifying what the DV is. Finally, you should describe your analysis plan. How are you going to analyze your data and which statistical tests do you plan to perform? This includes specifying things like the alpha level that you want to use for each test. How are you going to correct for multiple comparisons? Or do you want to use a 5% error rate or a 1% error rate or a 10% error rate? What do you think is sensible? It also requires you to specify things like data cleaning. What is an outlier and how you're going to remove outliers when they're problematic. Now we see that journals are increasingly starting to use these pre-registered studies. In this example, journal Perspectives on Psychological Science is using pre-registered protocols to perform large-scale replication studies, where a lot of people team up and perform a pre-registered replication of an existing study in the scientific literature. There's a clear benefit of pre-registering your studies, especially when the journal where you're going to submit your research allows for these pre-registered reports. So you can do this for a replication study, but you can also do it for very novel research. This means that based on the plan that you have, you will get comments from experts in the field that tell you how to improve your study design before you have put in all the effort to collect the data, analyze the data, and write the report. Compared to the traditional system where you only get all this feedback and these comments after you already did all the work, there's a big benefit because these peer reviews before you collect the data will allow you to improve your study design. So instead of doing all the hard work and then being told by reviewers that you made a mistake or you should have taken into account something that you didn't see, you can get this feedback before you collect the data. So this is a very efficient way to make sure that you perform a well-designed study where your peer reviewers agree that this is indeed the best approach to study a specific topic, and that the results will be informative regardless of whether they are statistically significant or not. And this is another very important benefit of these registered reports. When you've submitted your study design for publication, the peer reviewers give you some suggestions to improve the way that you want to study this topic. The editor of the journal will say, as long as you follow this pre-registered design, regardless of the outcome of the study, we will publish it. Now we know that publication bias is a huge problem in the scientific literature. There are way more study results that turn out to be statistically significant, as you would expect. The reason for this is that people don't publish their non-significant findings, or when they are submitted for publication, journals don't accept them. Now this problem is prevented by these registered reports, because people say, if you follow this plan, we will publish the results no matter what the outcome. So this is an important benefit, and if you do a challenging study, it's very worthwhile to consider following these registered report routes. There are some other benefits to pre-registering your studies. For example, you can do less conventional but more efficient designs. We already discussed how you can improve the statistical power of your test by performing a one-sided test. This also controls the error rate, but you're saying that you have a directional prediction. And if this is the case, then you can be more efficient in designing a well-powered study. However, people always think that there's something wrong with people who report one-sided tests because it's very often used as a way to reduce the p-value. So in this pre-registered report, you can write down that you have a directional prediction, you'll do a one-sided test, and you can reap the benefits of this directional hypothesis. Now, there are some places where you can pre-register your study design. You can visit the Open Science Framework or websites such as aspredicted.org. And you can see what's required for you to pre-register your study, which information you need to fill out. Now, if you do this, you can keep this pre-registration private, so you don't need to publish it online so that everybody can see what you do. It is possible, but you can just keep it private until the moment that you're going to submit your results for publication. And you can say, look, these are the results that I'm presenting, and you can see that this is exactly what I predicted when I designed the study. So in this lecture, we've seen that pre-registration is a novel but very useful solution to distinguish exploratory research from confirmatory research. And in doing so, it allows you to adequately control your type 1 error rates. In this lecture, we'll talk about the concept of effect sizes. I'll explain what they're good for, how you can use them, and why you should report them. And in the next lectures, we'll dive into more detail in two families of effect sizes, Cohen's d and correlations. Now, there are some people who think that effect sizes are in essence the main thing that we're interested in when we perform a study. There might be a lot of attention to the specific level of the p-value, but Cohen was one of the first to point out the importance of effect sizes in the scientific literature. And he says this is basically the main thing that you want to know, the primary product of a research inquiry. So it's important to always report these effect sizes, but not just to report them, but also to correctly interpret them. Effect sizes serve three main goals. First of all, they allow you to communicate the practical significance of the results. An effect might be statistically significant, but does it actually really matter in practice? Second, effect sizes allow you to draw meta-analytic conclusions. If there are a number of studies in the published literature, you can group all these studies together, calculate the meta-analytic effect size, and get the best estimate of the true effect size in the population. If we take a look at simulated studies, where we perform independent t-tests, and each group has 25 participants, you can see that there's quite a lot of variation in the effect size estimate. This forest plot illustrates effect sizes by the squares, and you can see that the squares jump around a little bit on the axis, and the axis is the effect size. So in this case, there's actually no true effect size. There's no true effect in the population, so the true effect size is 0. But we've drawn random samples from this population, and you can see that the effect size estimate within each individual sample actually differs from quite reasonably high and quite reasonably low effect size estimate, even though the true estimate should be 0. Now finally, effect sizes allow you to perform a power analysis. When we talk about controlling type 2 errors, it's important to think about what the true effect might be in the population. And an effect size tells you this, and you can use it in a power analysis to determine the amount of participants that the study would require to achieve a certain probability of finding a true effect if it's really there. Now this is an example of G-Power, which is free software, and I'm not going to explain exactly how you should use it. We'll talk about this in an assignment. I just want to highlight this field where you see that the effect size, Cohen's d, needs to be inserted if you want to perform the power calculations. There are different types of effect sizes. There are unstandardized effect sizes, which are basically just the difference that you've observed between two groups. Let's say you measure how quickly I can run down the corridor, you measure how quickly someone else runs down the corridor, you do this multiple times, and you want to see whether one or the other is fastest. Now in this case, there's no need to calculate any weird type of effect size. You can just use the time as an unstandardized effect size. People all understand how to interpret time. So time is a very logical skill to use, and if I'm 2 seconds faster, you know how you should interpret this. Now, not all research allows you to use unstandardized effect sizes. For example, think about people in the literature who study happiness. They might measure happiness by asking people, how happy are you at this moment, ranging from not happy at all, 1, to 7, very happy. Other people in the literature might use a 5-point scale to measure happiness. We can immediately see that a happiness score of 4 does not have any fixed meaning. It really depends on the scale that was used. So if we want to compare the size of a difference between these studies, we need to find a way to standardize these differences. And that's what a standardized effect size can do. Now, it's very important to interpret the effect size of a study. A statistically significant effect alone might not be real reason to worry. And this is a good example. There was a study performed by Facebook which influenced how happy people would feel. The way that they did this was either by removing some very positive posts on people's timelines, or they removed very negative posts on people's timelines. And then they measured the comments that people typed on Facebook and how positive or negative were the Facebook posts that people made. Now, there was quite a lot of attention for this study because the results showed that when people saw less positive information, people actually were slightly less positive in the Facebook messages that they posted themselves. Now, if we look really at the data themselves, and especially not at whether they were statistically significant or not, but at the effect size, we can see that the effect size here was a Cohen's d of 0.001. Now, that's a very tiny effect size. It was statistically significant because Facebook has a huge amount of data. They have millions and millions of Facebook posts to analyze. But the difference that they observed was so small that it was for all practical purposes almost meaningless. This implies that the effect that they observe was so small in the emotional connotation of the words that people typed that after 3,570 words, one more negative word was typed in the condition where people did not see positive feedback. Now, unless you type really, really long Facebook posts, this is not a noticeable effect at an individual level. This is only statistically significant over a huge number of people. But people were really worried, and there was even one blog post somewhere where they said, we know that mood is correlated with suicide, so maybe by experimenting on people, Facebook actually caused more people to commit suicide. But if you interpret the effect size, you can see that the effect is so tiny that this is basically impossible to have real-life consequences. So it's important to think that effects might be statistically significant, but they can be practically insignificant. Just because there is a true effect doesn't mean that we need to care or worry about it. On the other hand, it's also important to realize that small effects might have real-world consequences. In a meta-analysis in which researchers studied interventions for juvenile delinquency, they found that these interventions had a reliable but small effect size, Cohen's d of 0.11. Now, even though we consider this a small effect, it has real-life consequences that changes people's lives after the intervention. Instead of 50% of the young people leaving jails going on to commit more crimes, this reduces to about 45%. So this might be a small difference, but it's a very impactful difference for these people. It's also important to interpret effect sizes because they can be implausibly large. We talked about small effect sizes maybe being not really practically relevant, but big effects can also make you wonder what's really being studied and whether the results really make sense. Let's look at one example. In this study, researchers found a correlation between the suicide rate of white individuals and the amount of country music that was played on the radio. Now, this study won an award, an Ig Nobel Prize, which is a prize for studies that make you laugh and then make you think. Now, in this case, I think this study should make you think about effect sizes and how implausibly large effect sizes might indicate that this is not a reliable effect, but just a fluke. Indeed, it turns out that follow-up research was not able to confirm this result. And if you look at the effect size in this case, we can see that there's a correlation of 0.54, which is a large correlation. That's a sizable, noticeable effect. And it should make you wonder whether it's likely that listening to country music on the radio really has such a huge effect on the likelihood that people will commit suicide. If you see an effect size this large, you should say, I don't think that's very plausible. And you should make sure that you keep some doubt about the reliability of this finding. There are two types of families of effect sizes. A differentiation is made between the Cohen's d family, which are standardized mean differences, and on the other hand we have the R family, which are measures of strength of association, things like correlations. And in the next two lectures we'll go into more detail about both these families. Now in this lecture we talked about the importance of reporting and interpreting effect sizes. Effect sizes might arguably be the most important outcome of a study. The p-value will tell you something about whether there's a signal or noise, but even if there is noise, you might want to just accurately estimate that the true effect is almost completely zero. So you should always report effect sizes in your results sections, and more importantly, you should also always interpret the size of the effect. In the previous lecture we distinguished between two families of effect sizes, Cohen's d family on the one hand and R family on the other side. In this lecture we'll take a look at Cohen's d measures of effect sizes, standardized mean differences. Let's start with a practical example. Do movie ratings differ between websites? And if so, how much? Does it actually matter where you go on the internet to see how popular a movie is? Now this is my favorite movie of all time, Fight Club. I would definitely rate it a 10 myself, but I can understand that taste differs between people, so there might be some variation, and there might be a slightly lower average score than 10. Let's take a look at two different websites to see how people have rated this movie. If we go to the Internet Movie Database, we see that the score is a remarkably low 8.9. Well, okay. But if we visit Rotten Tomatoes, we see that the score that people gave Fight Club is actually a 7.3 out of 10. This is actually a big difference if you look at it like this, but we need to quantify this difference to be sure. Is this really meaningful or not? So let's calculate the standardized mean difference to find out. Now we have the two mean values. On the one hand, the Internet Movie Database, where the evaluation for Fight Club is an 8.9, and on Rotten Tomatoes, the average evaluation is a 7.3. Now conceptually, a standardized mean difference is the difference in means divided by the standard deviation. So here we have two means and we can subtract the one from the other to get the mean difference, but we also need to know the standard deviation. Now luckily I happen to know that if you look at all movie evaluations that are being done, the standard deviation is more or less 1.4 on these scales. If you have a 10-point scale, then the standard deviation you can expect if people evaluate movies is 1.4. So we can have the mean difference and divide it by the standard deviation to calculate the effect size. In this case, the Cohen's d is a 1.14, which, as we'll see later, is a very big effect. So it really matters which website you go to if you want to know whether people like a movie. A Cohen's d ranges from 0, no effect, to infinity. When there is no difference between two groups, the mean difference is 0, and you can divide it by any standard deviation you want, the effect size will remain 0. If the difference is really, really huge, then the effect size just goes up and up. Now let's visualize different effect sizes. If you don't have any idea of how to interpret an effect size, then there are useful benchmarks that you can use. And in this effect size, you can use the benchmarks of 0.2 for a small effect, 0.5 for a medium effect, and 0.8 for a large effect. In this graph, we see the visualization for an effect size of 0.2. It's clear that there's a difference. People in the one group are slightly more likely to have a higher score or evaluate a movie a little bit better than the other group. But you can also see that there's quite a lot of overlap. One individual from one group is very likely, even though they're from this group that on average has a higher evaluation for a movie, to like the movie less than someone from the other group. If we look at a slightly bigger effect size, a Cohen's d of 0.5, we can see the difference is bigger. There's still quite some overlap. And a Cohen's d of 0.8 is considered a large, meaningful effect. This is really a big effect size, and not many effects in psychology, for example, are as big as this. And even in this situation, there's still quite a lot of overlap. Sometimes you might be tempted to think that if there is a significant result, a significant effect, then everybody in one group should score higher than everybody in the other group. But these distributions clearly show that this is not the case. Even when we have a big effect, groups overlap quite a bit. Now, using these benchmarks, large, medium, or small, to interpret the size of your effect should only be used as a last resort. They're useful if you don't have anything else to go on, but it's typically already better to compare the effect size that you found to other related effects in the literature. You might be able to make a statement such as, well, compared to this type of intervention, this intervention has a smaller or bigger effect size. And this is better than just using these benchmarks. Sometimes this is not possible and these benchmarks are all you have to go on. So interpreting them in the minimum case should require these benchmarks, but hopefully you can interpret effect sizes in a slightly more meaningful way by relating them to effects in the literature. So conceptually, Cohen's d is the difference divided by the standard deviation. But there are a lot of small variations of Cohen's d, depending on the design that you use, for example, a within-subject design or a between-subject design. There's the Cohen's d for the population, if we would know the true value. And there's the Cohen's d for the sample, if you calculate the effect size based on a subgroup. And all these small variations might become a little bit complex, but they're important to keep in mind. They differ a little bit, and if you want to take a look at this, you can look at an article I wrote about this. I don't want to advertise my own work, but people apparently seem to find this specific article useful. And in this article, I give you all the different formulas for these slightly different versions of effect sizes. It's important to keep in mind which effect size you should use, especially when you perform power calculations. So this is a screenshot of G-power, which you can use to perform a power analysis. And in this case, we're performing a power analysis for a dependent test. There are two groups, but they are dependent. In this case, G-power asks you to fill in Cohen's dz. So this is one specific way to calculate the standardized mean difference. If you use a different way to calculate the standardized effect size, you might get an incorrect sample size estimate based on the power analysis. So keep this in mind. We have a difference between unbiased and biased effect size estimates. It turns out that if you just calculate Cohen's d, it slightly overestimates the true effect size. Especially when you have small sample sizes, this can be a little bit of a problem. Since you're most likely to use computer software to calculate the effect size anyway, it makes sense to always calculate the unbiased version of the d family effect sizes. In this case, it's called Hedges G. You can see that the G is just Cohen's d multiplied by a small correction. And this correction is only dependent upon the sample size. The larger the sample, then there's always no correction. But if you have a very small sample, the difference can be enough to be meaningful. You can also calculate effect sizes from the published literature. It's not always the case that researchers write down what the effect size is, that they have calculated this effect size and report it in the results section. If this is not the case, that's fine. In many cases, there's enough information in the results section to calculate the effect size yourself. For example, a Cohen's d can be directly calculated from the t value in the t-test and the sample size. Cohen's d for a within and a between design differ. You might have the same mean difference, but observations in a within design are correlated. This implies that if the correlation is really high, the effect size that's calculated based on the observation can be higher in a within design than in a between design, depending on the strength of the correlation. The difference in the Cohen's d in a within design and a between design is the square root of 2 multiplied by 1 minus the correlation. This implies that whenever the correlation between dependent measures is larger than 0.5, this difference factor is higher than 1, which means that d in a within design would be higher. This also means that the power in such a design is higher. In many psychological tasks, correlations between dependent measures are very high. It's a very strong correlation, which means that very often within designs will be more powerful than between designs. We already mentioned that it's important to report and interpret effect sizes. You can interpret effect sizes in relation to small, medium, and large benchmarks, but it's always better to try to interpret these effect sizes in relation to effects in the literature. Whenever you use these effects, or in power analysis, for example, or when you report them in your results, make sure that you realize that there are small differences within the D family, depending on the design that you've used. In this lecture, we'll continue talking about effect sizes, but now we'll focus on the R family of effect size measures. These include correlations, but also effect size measures for ANOVAs, such as eta squared. Now, if we look at the scientific literature, there's an example of an effect that can be described by a correlation, namely that the chocolate consumption in a country is related to the amount of Nobel Prizes that are won. Let's take a look at the data. We can plot the amount of Nobel Prize laureates on one axis, the amount of chocolate that's eaten in a country in the other axis, and then we see a strong positive correlation. In this case, I don't want to discuss how correlation does not imply causation. That's obvious. But here I just want to point at the size of the effect. As I mentioned before, it's very important to always interpret effect sizes. And in this case, a correlation of 0.8 is huge. It's such a big effect that alone should make you wonder whether this is real data or not. Now, if we look at correlations, we can again specify benchmarks for small, medium, and large effect sizes. A small correlation of 0.1 is visualized here. Again, we are using the visualizations from R Psychologist, a great website where you can play around with different visualizations for all sorts of basic statistical concepts, such as correlations and other effect sizes. So this is what a correlation of 0.1 looks like. A correlation that's medium effect size, is a correlation of 0.3, visualized here as well. And a large correlation, a benchmark, is set to 0.5. Now, correlations range from 0, no effect, there's no relation between two variables, to either -1, a perfect negative correlation, to +1, a perfect positive correlation. If you want to get a feel for what correlations look like if you visualize them, I can really recommend this website, guessthecorrelation.com, where they have gamified recognizing effect size measures. And if you play around with this website, you'll get a better understanding of what different effect sizes look like. Now, previously we talked about the Cohen's d measure of effect size. Both Cohen's d and correlations can be used to calculate meta-analysis. Therefore, it might not be very surprising that you can calculate Cohen's d into a Cohen's r. You can convert the one into the other. This is the formula that you might use for this. Again, I'm not going to go into too much detail about the specific formulas, but I just want to point out that it's possible to convert one effect size into the other effect size. And there are different spreadsheets online if you want to accomplish this. Now, in ANOVAs or regressions, we don't really use the simple correlation, but we use R squared, or for ANOVAs, eta squared, omega squared, and epsilon squared. These effect size measures express the proportion of the total variance that's explained by an effect. R squared and eta squared are slightly biased effect size estimators, and omega squared and epsilon squared are less biased. In this case, they're not perfectly unbiased, but they're pretty close. It turns out that epsilon squared is the least biased effect size measure, although omega squared is more often used and more widely recommended. Okada 2013 suggests that this difference might be due to a faulty random number generator in one of the original papers that compared these different effect sizes. I thought this was funny to point out, that even in this kind of simulation work, you can have reproducibility problems based on faulty random number generators. It doesn't matter too much. You can use both omega squared and epsilon squared. The difference between the two is actually quite small. Now, conceptually, these effect size measures answer a simple question. How much does the relationship between x and I reduce the error in the data? Let's try to visualize this. On the left, you can see a model where there is no relationship between the two variables. There's a horizontal line if there's an increase in one variable, there is zero increase in the other variable. Now we can calculate the sum of squares in this model where there's no relationship between the two variables. And the red squares indicate the sum of squares. So this is the total sum of squares if there's no relationship between the two variables. On the right, we allow for the model to have a relationship between the two variables. Now, if there's an increase in one variable, we see there's also an increase in the other variable. We again calculate the sum of squares, now indicated by the blue squares. This is the sum of squares of the residuals. And r squared is simply the sum of squares of the residuals divided by the total sum of squares. Now, if we use effect sizes for power analysis, you'll see that most statistical software asks for cohens f. Cohens f can simply be calculated from eta squared, using the formula that's on the screen here. You can also use statistical software to calculate cohens f from eta squared. A screenshot from gpower, free statistical software, is on the right. Now it's important to recognize that if you want to calculate cohens f in a within subject design and you're using gpower, there's something you need to keep in mind. In within subject designs, gpower expects a different version of partial eta squared than statistical software such as SPSS or R will provide. Now this is great free software, so I'm not complaining, but for some weird reason these researchers expect a different default than most other statistical software. This is only a situation if you use power calculations and within designs. In these situations, if you want to directly input eta squared, you need to click on the option box that's available on the screen. And if you click in this option box, then you get a specific menu where you can say, I want to input partial eta squared as in SPSS. Also, if you use different types of software such as R, then this is the option that you want to choose. If you forget to highlight this option, then the power calculations might be off quite considerably. Now, very often in experimental designs, you're interested in the partial variance explained by only one factor. For example, a factor that you manipulated. In these situations, you will calculate partial eta squared, or again the less biased partial omega squared or partial epsilon squared. Now, in a one-way ANOVA, eta squared is identical to partial eta squared. So if you're a little bit lazy, you don't have to report this small p, you don't have to type it in. It's easier just to say eta squared in these situations. Cohen has provided benchmarks to define small, medium, and large cohens f's. A cohens f of 0.1 is small, 0.25 is medium, and 0.5 is considered a large effect. Now we can use the formula that we saw earlier to calculate cohens f from eta squared, or vice versa. And then we can also create benchmarks for eta squared that's small, 0.0099, medium, 0.0588, and large, 0.1379. Now this is a lot of digits, and this is precision that's not really warranted, but this is a consequence of directly converting the effect sizes that Cohen used into eta squared. Now Cohen talks about eta squared when he defines these benchmarks, but he actually means partial eta squared. So you should use these benchmarks for partial eta squared, not for eta squared itself. Another important thing to keep in mind. Nowadays we also see more novel versions of eta squared, and one very useful one, which removes this difference between within and between subject effect sizes and can generalize between within and between subject designs, is generalized eta squared, developed by Olenik and Algina. Now I just want to point out that this exists if you're interested in reporting effect sizes, or if you use statistical software that automatically provides these generalized eta squared values. They're very useful and might be the best to report. In this lecture we talked about the R family of effect sizes, which allow you to quantify the degree of association between two variables. I pointed out some peculiarities when you use eta squared in within subject designs when you perform power calculations in gpower, and provided some benchmarks that you can use to interpret these effect sizes if you report them in your results section. In this lecture, we'll talk about how you can quantify the uncertainty surrounding estimates with confidence intervals. We'll talk about the relationship between confidence intervals and p-values and how to correctly interpret a confidence interval. Now, if we do research, we very often collect data from a specific sample with the goal to generalize to an entire population. It's very often not feasible to collect information from the entire population. If you examine people, then you cannot ask your questionnaire to everybody who's alive in the world. Now, sometimes it might be possible to get measurements from the entire population. Let's say that your population is all human beings who ever walked on the moon. Well, there are only 12 people who've done this so far, the 12 people on this slide. So if you want to know something about these 12 people, for example their length, then you can just calculate this. You don't need any statistics. You don't need to generalize to a population because you've measured the entire population. Now, in most research, this is not feasible. So you collect data from a sample and then you try to generalize from this sample to the population. And whenever you do this, there's always some uncertainty. Now, it's very important to always quantify and report the uncertainty surrounding point estimates, for example, an effect size measure. Whenever you report the statistics that's very important, such as an effect size, you have to report a confidence interval around this effect size estimate. We can visualize this. In this case, we have a correlation, and we've plotted the correlation between two variables. In this graph, we've visualized the uncertainty around the correlation between made-up data of an IQ of one twin and the IQ of the other twin. We can see that this IQ score is related. There's a positive correlation of 0.52. But of course, our correlation is an estimate from a sample. If we want to generalize this to the population, then there's always some uncertainty. And in this case, the uncertainty is illustrated by the blue area. The blue area illustrates a 95% confidence interval. But how should you interpret a 95% confidence interval? Confidence intervals are a statement about the percentage of future confidence intervals that contain the true parameter value. Now, this is not very intuitive. You might think that a single confidence interval contains the true population parameter 95% of the time. That would make sense, and if a non-statistician might come up with a confidence interval, the concept of a confidence interval, that's probably what we want it to mean. But that's not how they work. A confidence interval is a frequentist concept. It means that they apply to the long run. Now, in the long run, 95% of future confidence intervals will contain the true parameter value, so the true effect size, for example, in the population. Because this is counterintuitive, let's try to visualize it. In this illustration, which we again take from ourpsychologist.com, you can see many different confidence intervals for the same simulated study. We see blue dots, which are the sample estimates, the effect sizes from the sample that we collected, and the black line is the 95% confidence interval. Now, most of the black lines contain the true sample mean. In this case, the true sample mean is 0, and we see that most of the black lines touch upon 0. Sometimes they don't. We calculated a 95% confidence interval. So 5% of the time in the long run, we will get a confidence interval that does not contain the true population parameter. These are illustrated by the black arrows, and they are visualized by red lines. So the red lines do not contain the true population parameter. And this will happen in the long run approximately 5% of the time. Now, it's also clear that a randomly chosen single confidence interval here does not contain the true population parameter 95% of the time. And in the assignment, we'll focus a little bit more on this. So 95% of future 95% confidence intervals will contain the true population parameter in the long run. Never forget that this is a frequentist concept. A single confidence interval, after you collected the data, either contains the true population parameter or it does not. So in this case, you either have it or you don't, but you never know which it is. But in the long run, you can say that 95% of confidence intervals will contain the true population parameter. You can calculate a confidence interval around almost any estimate. But most commonly we calculate confidence intervals around means or mean differences or effect sizes. And it's very recommended to report them around effect sizes if you report effect sizes, which you should always do. So how do you calculate a 95% confidence interval or different size confidence intervals? Again, there's nothing magical about 95%. You can calculate a 90% confidence interval or a 99% confidence interval if you want to. For the 95% confidence interval around a mean, you calculate it by taking the mean and then adding or subtracting the critical z value multiplied by the standard error. Now it's okay if you don't immediately remember what a standard error is. The standard error is the standard deviation divided by the square root of n. And n is the sample size. So you can see that the larger the sample that we get, the smaller the standard error. And as a consequence, the smaller the confidence interval. If you want to calculate a 95% confidence interval around a mean, then based on the normal distribution, you would multiply the standard error by 1.96. This is a value that you see quite often in calculating confidence intervals. It's good to know that this is just the critical z value for a two-sided test. So you very often see this 1.96 value when people calculate confidence intervals. So as the sample size increases, confidence intervals become more narrow. Let's visualize this. In this graph, we can see an increasing sample size on the horizontal axis. It goes to 100, 200, 300, 400 participants in a two-sided t-test. On the vertical axis, we've plotted the effect size. And in this simulation, there is no true effect. In other words, the effect size is 0. And we see that the effect size estimate varies around this value of 0. The dotted lines are the 95% confidence interval. And we see that as the sample size increases, the 95% confidence interval becomes more narrow. In this simulation, the effect size actually stays very nicely between the 95% confidence interval, but sometimes, 5% of the time, the simulation will give you an effect size measure that falls just outside of these 95% confidence borders. Now, it's very important not to incorrectly interpret a confidence interval. And regrettably, the most intuitive interpretation is incorrect. You might feel that if you have a single 95% confidence interval, then 95% of future estimates will fall within this single confidence interval. But a confidence interval is a statement about future confidence intervals. It's not a statement about future estimates. It says that 95% of future confidence intervals will contain the true population parameter. You can take a look at how often a single 95% confidence interval will contain the true population parameter. Simulation studies have shown that if you perform many simulations, then it turns out that about 84.3% of single 95% confidence intervals contain the population parameter in the long run. And this is known as a capture percentage. So a single 95% confidence interval will capture the true value 84.3% of the time. Regrettably, this varies quite a lot. It depends. You never really know whether this is the case or not. So this is not a very usable statistic in itself, but at least it's one way to interpret a single 95% confidence interval. It gives you some idea about how often this single confidence interval will contain the true population parameter. About 5 and 6 times it will be the case. You never really know from a single observation. Now, confidence intervals and p-values are directly related. If a single 95% confidence interval does not contain 0, it automatically implies that the p-value is smaller than 0.05. Let's take a look at a meta-analysis where we've plotted effect sizes and confidence intervals so we can visualize this. In this graph, we see what's known as a forest plot. Every line illustrates a single study. On the horizontal axis, we see the effect size hedges G. The 4 studies vary in the effect size, illustrated by the yellow square, around an effect size of 0.43. Each effect size has a 95% confidence interval visualized by the black horizontal line. If we take a look at the third study from the top, we can see that the 95% confidence interval overlaps with the black vertical line at hedges G of 0. This implies that the third study did not yield a statistically significant effect because the 95% confidence interval around the effect size estimate contains 0. Now we've been talking about confidence intervals from a frequentist perspective. And here we have the slightly counterintuitive interpretation of confidence intervals in the long run. So 95% confidence intervals will contain the true population parameter 95% of the time in the long run, which is a frequentist interpretation. A more intuitive interpretation is found in Bayesian statistics, where people calculate credible intervals, or a slightly different version known as an highest density interval. And these can be interpreted in a more straightforward manner. A 95% credible interval contains all the values that you find most plausible. In this case, you're quantifying your belief. It doesn't mean that 95% of the true population parameters indeed fall within this area. It doesn't mean that in the long run you can expect 95% of credible intervals to contain the true population parameter. But it quantifies your belief. These are the values that you find most plausible. Remember that earlier we visualized the distributions of the prior, in this case the gray line, the blue dashed line illustrating the likelihood function, which together create the posterior distribution illustrated by the black line. We can calculate the 95% credible interval, the values that lie between the two shaded areas in the tails. Confidence intervals provide some idea of what will happen in the future. You can use confidence intervals to quantify the uncertainty in your estimates. Whenever you report important parameter estimates, such as effect sizes, you should always accompany these with confidence intervals. When you design a new study, one of the most important things to keep in mind is the sample size that you want to collect. We see that in many studies, sample sizes are too small. And I want to give you some practical advice on how to decide upon a sample size for a future study that you'll do. So if you would design a new study, how would you determine the sample size? Take a moment to think about this. There are different approaches to do this, and we'll talk about them in this lecture. What I used to do when I was doing my PhD was either use exactly the same number of participants as a previous study had used, or I would use a heuristic. In my time, it was quite common to use a sample size of 15 participants for each between subject condition. Nowadays, this number has increased a little bit. I see that people very often use about 25 participants for each between subject condition. But is this sufficient? And if not, what should you do instead of relying on these heuristics? Now first, let's realize what the problem is if you collect small samples. Small samples always have large variation, leading to very inaccurate estimates. But when you perform a hypothesis test, they also lead to high type 2 error rates, which means that you perform a study, you do a statistical test, and even when there is a true effect, the test result is not statistically significant. It's important to prevent this, both type 2 errors and inaccurate estimates. This is a nice visualization by Schoenbrod and Perugini, who show how the variation in data decreases as the sample size becomes larger. From the left to the right, we see a continuously increasing sample size. We also see a black line, and in this case, the black line is actually the effect size estimate from a study they performed as they collected more and more data. So the effect size was calculated after every participant, and it's plotted here as a black line. You can see that there's a huge drop in the effect size. And what they show is that actually such variation is possible because small samples have very large variation. I refer to this as sailing the seas of chaos into what Schoenbrod and Perugini named the corridor of stability. On the left you see huge waves. If you have small samples, then your data is riding these huge waves. Effects can be very large or very small. The variation is substantial. Now, as you enter the corridor of stability, as Schoenbrod and Perugini call this, you see that the variation becomes much less severe. There's still some variation around the true effect size estimate, but at this point you're making very accurate estimations. Now we see that researchers fail to take the sample size into account when they design new studies, and this is nothing new. We've known this for about 50 years, and only now is it very slowly changing. In certain literatures where sample sizes are very expensive, so if you want to collect a large number of people, you have to have a lot of money, such as neuroscience, where we put people in fMRI scanners, we see that there's really a huge power failure. Studies are severely underpowered. Interestingly, people have been saying this for years and years, and there are even papers that say that the studies of statistical power don't have any effect on the power of studies. This is slightly depressing, because here I'm talking about how you should design well-powered studies, even though past research has shown that this does not have an effect on what researchers really do. But on the other hand, we see that things are now really changing. More and more journals are requiring what's known as a sample size justification. You need to explicitly write down why you selected a specific sample size. So I seriously think that in the future we'll see a big change in this specific area. We see that studies in psychology often have very low statistical power. Estimates average around 50%, which means that even if you have a true hypothesis, you only have a 50% probability of actually observing a statistically significant finding. I think that if people realize this, they would seriously reconsider doing the study, because they only have a 50% probability of finding an effect when it's there. That doesn't seem to be worth all the effort to collect this data. Now, one reason for low-powered studies is that people don't really think about how to design their study, and especially the sample size of their study. But people use heuristics instead. Now, heuristics are always wrong. You should never rely on heuristics to plan the sample size, no matter what the recommendation of this heuristic is. Whether it's 10, 20, 50 people, you should always use a better approach, a more informed justification of your sample size. Nowadays, journals ask you to do this, so you need to justify the sample size of a study. The justification depends on the goal that you want to achieve. Let's consider different goals. In this graph, we can see again correlation between two variables. We see a rather wide confidence interval. In this case, there are only 10 observations, so the confidence interval is really wide. If we increase the sample size to 100 participants, we see that the confidence interval becomes much more narrow. If your goal is to design a study that will accurately estimate the true effect size, then having a sample size that allows you to achieve a certain accuracy is a good goal. So one approach is to plan for accuracy. Select a sample size based on the width of a confidence interval. A classic paper on this is Maxwell, Kelly, and Rausch. I can recommend that you read this if you want to know how to design studies based on accuracy. The second approach is to design a study so that it will have a specific statistical power. Now, we already saw this graph earlier on in the course, and in this simulation we have 50% power, which means that 50% of the p-values end up in the leftmost bin. Now, you might think this is too low. You want to design a study which has much higher power. For example, 95% power. So you can design a study where you plan for power. You select a sample size based on the probability of observing a p-value smaller than 0.05. And in these cases, you would do a priori power analysis based on an expected effect size. If we take a look at the power for an independent t-test with a Cohen's d of 0.5, we can see that the sample size that you need to have a substantial power can become quite large. And very often, if people start to perform power analysis, their first complaint is that the sample size that's recommended is much larger than they think is necessary. Now, people seem to have some intuitive feel of the sample size that they need to achieve 50% power. As we see, the literature mainly has studies with about 50% power. So in the beginning, you might be surprised by how many people you need. If you want to have about 95% power, you would need a sample size of about 100 people in each condition, which is quite a lot more than the 15 participants in each between subject condition that I designed when I was doing my PhD. So be prepared for slightly larger sample sizes. Now, when you base your power analysis on an effect size from the published literature, be very careful. We know that publication bias inflates effect size estimates in the literature, so you always want to be a little bit more conservative. A power analysis should be a starting point for designing the sample size in a future study. It should not be the end point, so always be informed by more than the power analysis itself. If you perform a power analysis, always use unbiased effect size estimate in the power analysis, so hedges G, epsilon, or omega. If effect sizes are uncertain, there's not a lot to go on in the published literature, or there's nothing comparable in the published literature, then sequential analysis are one way to let you look at the data as it comes in, while controlling your type 1 error rates. So if there's huge uncertainty, but you still want to achieve a statistically significant result, that's the goal, then instead of doing an a priori power analysis, you can use sequential analysis and collect data until you find a statistically significant effect, or until you don't want to collect more participants. Now, instead of planning for accuracy or power, it's perfectly fine to plan for feasibility. You don't have infinite resources, infinite amount of time or money, or sometimes the population that you want to collect data from is very, very difficult to reach. So in these cases, the feasibility of collecting a large sample size is limited by how easy it is to find participants. So it's perfectly fine to select a sample size based on the time, the money, or the participants that you have available. This can also be a way to plan a study. This is just the best that you can do given the resources that you have. And that's perfectly fine. Of course, in these situations, it might be that the statistical power is low, but in that case you might just want to estimate the effect size instead of performing a statistical test. You can also use Bayesian statistics. In Bayesian statistics, you don't have to specify the sample size before you start. You can collect data and continuing data collection until whenever you want. This quote by Edwards, Lindman and Savage says, "It is entirely appropriate to collect data until a point has been proven or disproven, or until the data collector runs out of time, money, or patience." If we design a study based on the statistical power, this is a frequentist approach to designing a study and determining the sample size. But in Bayesian statistics, you just quantify the evidence that's in the data. And if you're not happy with the evidence you have, you can always collect more data. So Bayesian statistics is much more flexible. You can determine the sample size any way you want. On the other hand, there's no easy way to control type 1 errors. It's not entirely uncontrolled, but it's just much more difficult to quantify the type 1 error rate directly. Nowadays, it's becoming increasingly important to justify the sample size of a study that you're designing. In the past, we've seen that people designed underpowered and inaccurate studies, and in the future, this really needs to change. The sample size is a very important aspect of the design of a new study. Don't ignore it. In this lecture, we'll talk about P-curve analysis, a recently developed meta-analytical tool that allows you to judge the evidential value in sets of studies in the published literature. What do p-values look like from 100 studies where there is no true effect? We've discussed this in an earlier lecture. If you remember correctly, p-values are uniformly distributed if there's no true effect. Now, if you've watched enough medical series, you know that a flat line is no good news, right? So in this case, if we see a p-value distribution that's uniformly distributed, then nothing is going on. What do p-values look like from 100 studies where there is a true effect? Well, in this case, we know that the p-value distribution depends on the statistical power of the test. In general, we can expect more low p-values, around 0.1 for example, than high p-values, around 0.5. Even though all these p-values are statistically significant, they're all smaller than 0.05, they're not all equally likely if there is a true effect. We should find low p-values more often than relatively high p-values. P-curve analysis allows you to test whether a set of p-values has evidential value. In this case, evidential value is defined as, does the p-value distribution look more like a uniform distribution, where there's no true effect, or more like a p-value distribution where there is a true effect? An important benefit of p-curve analysis is that it's a key to the file drawer. The test is only performed on p-values smaller than 0.05. Given publication bias, where we know that studies are much more likely to be published when they are statistically significant than when they are not statistically significant, an important benefit of p-curve analysis is that you only need the statistically significant study results to perform the test. So you can perform it even though there is publication bias, and that's a huge important benefit. Another useful thing about p-curve analysis is that you can perform the test online. You don't need any statistical software. Go to the online test, enter test statistics, and perform all the required calculations. The question we're trying to address with a p-curve analysis is, does the p-value distribution look like one with or one without a true effect? A good moment to perform a p-curve analysis is before you set out to build on studies in the published literature. You might want to know whether these studies in the published literature are just there due to publication bias, and they're all basically type 1 errors, there's no true effect, or whether the results look robust enough to build on. So we're trying to differentiate between these two possible p-value distributions, uniform or what's known as right-skewed. The green line in this case illustrates a true effect. Now let's take a look at an example. I performed the p-curve analysis of two related lines of research. On the one hand, elderly priming studies, and on the other hand, professor priming studies. Now, the evidence in these studies was debated by the publication of failed replication studies. Some people responded to these failed replications by indicating that there are many different studies in the literature that show related effects. Now, this is a valid reply, except that if you want to say that there's evidence in the published literature, then you need to quantify this. You can do this either by performing a traditional meta-analysis, or you can perform a p-curve analysis. And that's what I did in this case. Now, this is the p-curve analysis for elderly priming studies. Elderly priming examines the idea that if you expose people to elderly-related words, such as bingo, gray, or Florida, this will influence their behavior. More specifically, it will influence their walking speed. The idea being that elderly people walk more slowly. So people who were primed with elderly-related words would walk more slowly to an elevator than people in the control condition. If we take a look at the p-value distribution of the studies in the literature, we see that the p-value distribution is not uniformly distributed. It's not right-skewed. No, actually we see that a lot of these p-values are only barely significant. This is not an indication that the studies published in the literature provide support for the hypothesis. The hypothesis might still be true, but the data that we have available does not give us any reason to believe that this is a true effect. Now let's take a look at professor priming studies. In this line of research, people are asked to think about a professor. Or in the control condition, they're asked to think about a group that's stereotypically seen as less intelligent, such as soccer hooligans. The idea in this study is that participants who thought about a professor are more likely to perform better on a general knowledge test, such as Trivial Pursuit, than people in the control condition. If we look at the p-value distribution, in this case, the distribution is very similar to that we would expect when there is a true effect. Now this illustrates how useful it is to perform a p-curve analysis before you want to build on studies in the published literature. Let's say that you're interested in priming effects. Would you build on elderly priming research, or would you build on professor priming research? Now these p-curve analyses do not prove that professor priming is a real effect and elderly priming is not a real effect. But if you're thinking about doing research on priming, and you have to decide between these two research areas, then it's a much better bet to build on professor priming related studies than elderly priming studies. You can also use p-curve analysis for small sets of p-values. You have to take a little care. When you have a small number of observations, you have low statistical power for any test, also for a p-curve analysis. But sometimes the data is so clear that even with a small set of studies, you can prevent yourself from following up on unreliable research. Let's take an example. In this publication, researchers looked at the effect of reading literary fiction on theory of mind. How much do you, for example, empathize with other people? The researchers performed 5 studies, and they provide a table with the critical test results for each study. We're always interested in the main effect of condition, and I've highlighted the test results here. We can see that for the first study they observed a p-value of 0.01. For the second they have observed a p-value of 0.08. This test result will be ignored by the p-curve analysis because it only focuses on p-values smaller than 0.05. Then for the remaining 3 studies we see p-values of 0.04, 0.04 and 0.04. Let's perform a p-curve analysis on this data set. We can see that the p-value distribution is not as you would expect if there is a true effect. And indeed, the statistical test tells us that the evidential value of this set of studies, if any, is inadequate. This does not mean that the theory is false. It could still be true, but the data that we have available in this publication does not allow us to conclude that the hypothesis is supported. The reason that I'm giving this example is not that I want to point out that some people publish sets of studies that are not reliable. It happens. But it's very important for you to know that you can use p-curve analysis to identify sets of studies that are less reliable than others. When I was presenting about p-curve analysis in a workshop I taught, one of the PhD students in the room was performing a p-curve analysis on exactly this set of studies. This PhD student was trying to replicate these studies for over a year, but has been unsuccessful. So I think it's very important to perform a p-curve analysis before you try to build on studies in the literature. Because otherwise you might waste a year trying to build on research that is not as reliable as you think. Now remember, when a p-curve analysis says that a set of study lacks evidential value, the theory might still be true. The data just don't provide evidence for the theory. P-curve analysis allows you to test whether a set of studies in the published literature yields a p-value distribution that looks more like the one you would expect when there is a true effect than when there is no true effect. Using p-curve analysis before you decide to build on studies in the published literature might allow you to see how robust these findings are and prevents you from building on unreliable results. In this lecture we'll talk about philosophy of science. I'll give a brief overview of the history of philosophy of science. Now this is a topic that you can spend an entire course on, and if you're interested I highly recommend you do this. But you should at least know the basics. Can we ever have something that's objectively true? Do we know whether something is a science or not? These are important questions to consider. Now if we ask ourselves the question, what makes something scientific, then we're asking what is the demarcation criteria? What differentiates between science and pseudoscience? Do you think that astrology is a scientific discipline? Should we use tax money to fund research on astrology? Do you think that precognition, studying whether we can predict the future or not, is a science, and should we fund it based on tax money? Do you think that my own discipline, experimental psychology, is a science, and should we fund this? You see that the question whether something is a science or not has real-life consequences. If we think about demarcation criteria, then different people have different opinions about whether we can say that there's a difference between science and pseudoscience. Popper says that if a theory is falsifiable, then it's scientific. And this is the demarcation criteria according to Popper. But not everybody agrees. For example, Lakatos says that a given fact is explained scientifically only if a new fact is predicted with it. You should not just describe things that you see, but your new descriptions are scientific explanations when they can also predict new things, when they can explain new information. There are also people who give up on trying to differentiate between science and pseudoscience. A well-known example is Paul Feyerabend. He says that given any rule, there are always circumstances when it is advisable not only to ignore the rule, but to adopt its opposite. So there's never a rule that you can follow that will differentiate between science and pseudoscience. Anything goes. If we draw inferences from data, then there are logical ways to do this and illogical ways to do this. In propositional logic, one valid rule of inference is known as the modus tollens. In other words, denying the consequent. Let's take a look. If the modus tollens is used, we have a line of reasoning that goes as this. If P, then Q. Not Q, therefore not P. Let's make it a little bit more concrete. If we have a theory, then we should observe some data. Then we collect some data, but we do not observe the data that we predicted. From this, we can deny the consequent. Therefore, not the theory. A very often illogical way of drawing inferences is known as affirming the consequent. Now, this is not a valid rule of inference, although it's tempting to use. It goes like this. If P, then Q. We observe Q, therefore P. Now, this might look like it's logical, but it isn't. Let's look at some more detail. If we have a theory, then we should observe some data. We observe the data, and then we conclude that therefore the theory is true. Now, this might still look like it's valid, but it isn't. Let's make it even more concrete. Let's say that I conclude that if I'm a man, then I'm also a human. I observe that I am a human, and then I conclude that therefore I must be a man. But this last step is not valid. I could also be a woman or anything in between. A theory can be either refuted or corroborated, but you can never prove a theory. Now, this is important. We can never have certain knowledge. We can aim for it, but we can never achieve it. It's easier to refute a theory, and this is based on Popper's idea of falsification. So you can have a conclusion where you falsify a prediction. For example, if we look at the prediction all swans are white, now no number of sightings of white swans can ever prove the theory that all swans are white. However, if we only see one black swan, this will disprove our theory that all swans are white. So you see that falsification is a very potent tool to reject theories. Now, we can never accept them. We can observe observations that are in line with our theory, but we can never prove it. However, when we use inferences based on statistics, then falsifications are never really black or white, as the case with black swans. If you see a black swan and you have a clear view, then you can be pretty sure that this is not a white swan. You might even get a feather, try to wash it, see that the black doesn't come off, and then you have a solid observation that black swans exist. In statistics, we always work with probabilities. We have a certain probability that the data we have observed is surprising, for example. We have a certain probability that there is no true effect. Now, these kind of statements are never completely black or white, so it's always more difficult to falsify a prediction. Furthermore, we wonder whether we actually reject theories after a falsification, after a single falsification. And Lakatos argues that we never do this. People have some sort of feeling for a theory. They like a specific theory and they want it to be true. And this is perfectly fine. You can try to find support for it in different ways. Now, there are good reasons to stick with a theory. When a theory makes very, very good predictions, then a single observation that's not in line with your predictions is no reason to give up the entire theory. This statement by Stevens is rather nice. It says, the lesson of history is that a bold and plausible theory that fills a scientific need is seldom broken by the impact of contrary facts and arguments. Only with an alternative theory can we hope to displace a defective one. So it's perfectly fine if you sometimes observe a finding that's not in line with theoretical predictions. You don't have to throw your theory out of the window. If you have a strong theory that makes good predictions in other fields, there's no reason to give it up until you have a better theory. So if there's a falsification, if one of these predictions don't hold up, then what is exactly falsified? Is it the theory itself, or are there auxiliary theories, assumptions that you make about the data collection process, for example? Now let's say you do an experiment on some people and you have a theoretical prediction, and it's not supported by the data. Now you can either distrust your theory itself, or you can say, well, maybe something else that I assumed was going on didn't happen as I predict. For example, maybe your participants were very, very tired. They didn't process all the information you provided, and as a consequence, you didn't observe the effect that you predicted. Now in these situations, you might not throw away your theory. You might say, well, some of the assumptions I made about how much attention participants were paying to the experiment, those assumptions are violated. Let's try it again. Let's try to boost the attention levels of participants and see if we can find the expected effect. According to Lakatos, we have a core theory, and around this core theory there's a protective belt of auxiliary hypotheses. These are assumptions that you make about the research process, and you can give up some of these assumptions or change them. In this sense, you can keep your core theory even if your prediction doesn't pan out by changing some of the assumptions that you make. Now, of course, when you do this, you enter what's known as a degenerative research line. It's fine to make an ad hoc assumption, saying, well, it's true, but only if. But if you have to keep doing this and keep doing this, then your theory is not making new predictions. There are no new facts that are predicted with the theory that you make. You're just trying to change the theory every time when a failed prediction emerges. What you ideally want is to turn this into a progressive research line. A first failed test is perfectly fine. You can slightly change your theory or one of the assumptions you're making, but then this should lead to a progressive research line. There should be new facts that you can predict with your improved theory. When this is not the case, it's perfectly fine to keep trying, but after a while, you enter a research line that's not giving anything new, which happened with astrology in the past. So according to Lakatos, something like astrology would not be a scientific discipline because it never turned into a progressive research line. They're only ad hoc changes to the theory every time when a failed prediction emerges. Now, there are some people who doubt whether we can have an objective science altogether. So they say the quest for an objective truth is a nice try, but we'll never really reach it. One of them is Thomas Kuhn in his book, The Structure of Scientific Revolutions. He says that observations are always theory-laden, not objective. There's no such thing as an objective view at the world. We always look at the world with certain assumptions, and these assumptions color the way that we do our research. He goes as far as to say that the proponents of competing paradigms practice their trades in different worlds. What he means is that it's possible for researchers to have different theoretical backgrounds, and they will look at the world in completely different ways that you cannot unify. He talks about how people practice puzzle-solving science, which is basically normal science, as science should progress. And this is followed by a paradigm shift, a revolution in science. And after such a scientific revolution, we look at the world in a completely different way. And after a scientific revolution, we cannot interpret the data that we collected before this paradigm shift. Things completely change. So there's no objective knowledge. Things always depend on the specific paradigm that you're in. According to Kuhn, science is not cumulative, but it's revolutionary, based on subjective reasons. These can be social norms or ideas that people have. So it's not that science will always just progress and become better and better, the idea that Lakatos is expressing in his progressive research lines. No, instead there's just a revolution every now and then when we have a completely different paradigm within which we practice science. More modern viewpoints on philosophy of science acknowledge that scientific knowledge is a social product. For example, Helen Longino talks about how we have no objective knowledge, but there is only intersubjective criticism what constitutes the objectivity of science. So there's no objectivity outside of the social enterprise that science is. What's important, according to Longino, is public avenues for criticism, for example, peer review, when you submit your paper for publication, what's important is that there's room for peers to criticize your finding or improve it if possible. There should be shared standards. We should have some idea of what we're doing, a tool set that we use to evaluate evidence. There should be open re-evaluation. So if there's criticism and there are new insights, a scientific discipline should change. Again, this is not something that happens in astrology. There's enough criticism on astrology, but it never really changed in the last decades. And finally, what's important for this social intersubjective objectivity is that there's equality within peers. If you have an informed researcher that knows what he or she is doing, then these people should have equality in their interaction. It should not be the case that one person can determine this is how it's going to be because I'm the most powerful individual here. In this lecture, we briefly talked about philosophy of science and different perspectives that philosophers have on what makes something scientific. Personally, I think the idea of a progressive and a degenerative research line is quite useful. When you make a prediction that doesn't pan out, you're in trouble. You have to try to turn this into a progressive research line in the future. But overall, there's no clear single answer on whether we can ever have objective knowledge. In this lecture, we'll talk about which hypothesis you might want to test. In science, we often rely on null hypothesis significance testing. But there are also some people who say that testing the null is very boring because the null is always false. Is this criticism valid? And if so, which hypothesis might we want to test instead? Let's take a look. In science, we very often use a null hypothesis significance test. Is the data we have observed surprising, assuming that the null hypothesis is true? This practice is also often criticized. One of the critics of this is Cohen, who says the null hypothesis, taken literally, is always false in the real world. So if the null is always false, what's the big deal about rejecting it? So is this really true? Is the null hypothesis always false? Well, not really. Sometimes with very large sample sizes, some effects are pretty darn close to zero. We can take a look in the Many Labs dataset. Many Labs project was a big replication study where 36 different laboratories all replicated the same set of studies. So here every line is a different study, and if we look at the bottom, we see that at least 2 of these studies with more than 5,000 participants yield an effect size that is indistinguishable from zero. Now the question is whether if we would continue to an infinite number of observations, there will be a statistically significant effect. We don't really know, but it seems unlikely that this really matters in practice most of the time. It's important to distinguish between one situation where the null is a very reasonable hypothesis and a situation where the null is not a very reasonable hypothesis. If we use random assignment to conditions and we successfully accomplish this, then there is no reason to assume that there is a difference between 2 groups unless the manipulation that we use in our experiment actually has an effect. And if it's possible that the manipulation has no effect, and this is a question you're interested in, then we can test the null. However, we also sometimes test for measured variables. An example of a measured variable is gender. People have often enter the lab with a specific gender. They have the same gender throughout their lives, so it's not something that you can easily change. If you want to look at differences between men and women, for example, then you cannot directly manipulate this. You can only measure this variable and look at the differences. Now let's see why this matters. We can compare the effect of random assignment and measured variables in the Many Labs dataset. Let's take a look at one manipulated condition. In this case, we look at the anchoring condition people are randomly assigned to. Now in anchoring, people receive either a high or a low number as a manipulation. Then after that, they all make the same estimate about something they're uncertain about. And what the literature shows is that this estimate is influenced by the height of the anchor. If they first get a very high number, their judgment under uncertainty is increased a little bit. And if they get a very low number, then their estimate is slightly lower. Now we can take a look at whether being assigned to the high anchoring condition or the low anchoring condition has an effect on any of the other tests that participants did. So they did a lot of tests. I'll look at 10 different outcomes and see whether the random assignment to the anchoring condition has an effect on any of these other dependent variables. We can also take a look at whether there are gender effects. If we do this, we see that the anchoring condition only has an effect on one specific dependent variable, the anchoring effect that it's intended to influence. However, if we look at gender effects in this data set, we see that 7 out of the 10 dependent variables here all show a gender effect. That's a very high number. So why is this the case? We don't know. There are probably things that vary with gender that also influence the other dependent variables that we're measuring. Now, in all these studies, there were also manipulations, and these were the main interest in the test. But we see that gender effects are always present, or very often present. So whenever we have a measured variable, it might be less interesting to test the null. Very often, the null is not true. It's not a very interesting thing to see. So why is this the case? There is systematic noise in your data. Licken and Mail call this the CRUD factor. As long as you measure enough observations, these systematic differences that are present in your data will always yield a statistically significant result. Now remember that in the Many Labs project there were more than 5,000 participants. So this is a very large data set, and these tiny systematic noises will lead to differences on your dependent variable. So these things are not completely interesting. They might be, but it's very difficult to pinpoint the origin of these effects. It might just be some sort of noise you're not interested in. So whenever we can manipulate a factor, the null might be more interesting, but in these cases of measured variables, there's always the CRUD factor to keep in mind. So we can conclude that, in principle, all models are wrong, but some models are useful. This is a statement by George Box. What he means is that you can have a model that can be a useful test. After randomization is possible, so when you can randomly assign people to conditions, the null can be a useful and a true hypothesis that you're interested in. But without randomization, the alternative, saying that there is an effect, is not a very bold prediction. There very often is an effect. If the null is rarely true, then refuting the null says very little about the truth of a theory. You have to make a better prediction. You have to do something more than just testing the null hypothesis. The null hypothesis itself is what we know as a very weak hypothesis. Let's give an example. If I predict that it will rain next year in April, then that's not a very strong hypothesis. It's very easy to say that this is true, this is going to happen, and you won't be impressed if I make this prediction and it turns out to be true. You can also make a strong prediction, have a strong hypothesis. If I say that it will rain 7 millimeters on April 2nd next year, and it turns out that this prediction is true, now that will get me a job as a very good weatherman. So null hypothesis significance testing rejects the null compared to any alternative, any other prediction goes. And that's not very exciting in some situations. In these situations, just as with the weather, you want to make a point prediction. You want to say, this is what I predict. I don't just predict an effect, but I can predict, with my theory, which is pretty good, an effect of a specific size. And if you can accomplish this, that's much more impressive. So confirming strong hypotheses gives a theory greater verisimilitude. And that's a very difficult word for something that's akin to truth-likeness. It gets you money in the bank. This is a finding that will increase your confidence in the theory. And that's what you want. Now let's play a small game. I'll ask you what the rule is underlying the numbers that are presented on the screen. You see the numbers 2, 4, and 6. You can test the rule by naming any other number that you think will follow the rule. Come up with any number you want, and I will say, yes, it follows the rule, or no, it will not follow the rule. Take a moment to think of any number you want. Which number would you like to test? Let's say that you come up with the number 8. This makes sense, right? You see 2, and you add 2, you got 4, you add 2, you got 6. So maybe this is the rule, just adding 2. So if you would test 8, I can say, yes, That's a valid number. It follows the rule. You might have a different theory. You might say, well, maybe it's 4 plus the number that comes before it. So then we have 4 and 2 and 6, and then the next number might be 10. So if you want to test the number 10, perfectly fine. Yes, it also follows the same rule. But you have not learned a lot. Is this really the underlying rule? What would happen if you would say 7? Now that's a very interesting question, because in this case you're not trying to confirm the rule that you have in your mind. You're trying to disconfirm, falsify your prediction. If I say 7, if you say 7, then I'd say yes, that's also following the same rule. Because in this case the rule might be increasing numbers. As long as the next number is an increasing number, it follows the rule that I have. And you would never discover this if you just try to confirm the idea that you have in your head. So whenever we do a study and we try to confirm our predictions, then this confirmation bias can be a systematic error in inductive reasoning. You cannot learn whether your theory is actually true if you only set out to confirm your predictions. Instead, you should try to have stronger theoretical predictions where one of your predictions can be falsified. One way to do this is to set out to test 2 competing predictions. Either the one hypothesis is true or the other, but they can't both be true. So when I find some data, I can say this is at least in line with the one theory, but is not in line with the other theory. So this is already a more interesting comparison to make. This is known as strong inference, crucial experiments that can exclude one alternative hypothesis. And this is a very good way to have scientific progress. According to Plot, who talks about strong inference, you should always ask yourself the question when you design a study. But what experiment could disprove your hypothesis? That's the main thing you should set out to do. Of course, you might not feel like disproving all the nice ideas that you have, but for science, this is a very good thing to set out to do. So we've seen that people sometimes criticize null hypothesis significance testing because it's a very weak prediction. Anything goes as long as the null is not true, and when you don't have random assignment, even this idea of the null being true is not a very interesting hypothesis to make. So you should try to set out to make strong predictions, test competing hypotheses whenever this is possible. In this lecture, we'll talk about theory construction. In most of the course, we talked about statistical inferences, drawing inferences from data. But of course, what we really want to know is whether your theory is true or not and can predict something. Generating a good theory is difficult, and it depends a little bit on the specific research area you work in. But we can give some general recommendations. Now, in most of this course, we've been talking about statistical hypotheses and drawing statistical inferences. But as a researcher, of course, what you want to do is draw theoretical inferences. To do this, you, of course, first have to have a good theory that you can use to create a statistical hypothesis. So we see that statistical inferences and theory generation are basically 2 sides of the same coin. A scientific theory is a set of testable statements about the relation between observations. And whenever we collect data, we do so with the goal to test some of these statements to try to make an inference about whether the theory has good predictive power or not. Now, we focus a lot on testing these theories, but not a lot on theory construction. This is an important topic in itself. It's sometimes more difficult to teach, but it's really important to keep in mind that theories are really what's driving the goal of doing research. I will give some suggestions on how to come up with good ideas to generate theoretical predictions. Some of these are based on this book, Theory, Construction and Model Building, which focuses a lot on how to do this within the social sciences. So if you're interested in this topic, I would highly recommend that you take a look at this book. So which approaches can we use? One used approach in science is to come up with a thought experiment. A very well-known thought experiment is done by Einstein when he asks himself, what would you see if you could travel at the speed of light? So by coming up with this thought experiment and thinking about what would happen, you can create theoretical predictions that are testable. Another approach that we use in the social sciences is sometimes to rely on your personal experiences. What happens to you? And can you come up with a theoretical prediction based on something that someone tells you? One example is Stanley Milgram's mother. Over dinner, she complained that nobody in public transport would give up their seats if she entered the public bus. So Stanley Milgram was interested in the social norms in cities, and he looked at whether people would actually give up their seats depending on how you asked these questions. And he found that 56% of the people actually would give up their seat if you nicely asked. Another approach is to try to empathize with other people. Put yourself in someone else's shoes and think what drives the behavior of this individual. In psychology, a well-known example of this is the question how it is possible that people who worked in concentration camps did what they did. This inspired a lot of theory development on authority, for example. You can also use observations. Let's say you go out and you buy a car and you look at the car salesman. What do these people do to sell you a car? What kind of tricks do they use, and how can this inform you about persuasion and theories about how to make most persuasive arguments? Another approach we often use is to rely on metaphors. Now, a metaphor should never be a replacement of an existing theory, but it can be used to inspire theoretical reasoning. In memory research, one of the theoretical models is the model of memory like a storage bin. Whatever you put in last in a storage bin is also most easily retrieved. So one theoretical prediction based on this metaphorical line of reasoning could be, is it also the case in human memory that whatever we store last is most easily retrieved? What's always a good idea as a scientist is to ask why and how like a 3-year-old. Don't take anything for granted. When you read about theories in the literature, always ask, why would this be the case? What's going on? What's the underlying mechanism? This can inspire new theoretical questions. Finally, a good idea is to have broad interests as a scientist. We see that many of the most groundbreaking ideas come from introducing ideas in other scientific disciplines into your own research line. You don't have to limit yourself to other scientific disciplines. You can also be inspired by movies or books or whatever you see and hear. Now, after you have generated some hypothesis and some theory, it's good to try to formalize this theory and this theoretical prediction as well as possible. One idea is to use multiple modalities to do so. So you can use words to describe your theory, figures and numbers. For example, let's say we have the theoretical hypothesis that students are happier than teachers, but especially on hot days. The idea being that on these hot days, students are free to go out and enjoy the weather, while teachers are, of course, working inside, preparing your next lecture or grading your assignments. So we can visualize this in the form of a simple graph. We can have a statistical hypothesis saying that this is an ANOVA, and then we should find an interaction. Or you can even try to specify the numbers that you expect to observe in each of the conditions in this design. When you define your theoretical prediction, it's always good to think about the boundary conditions of the effect that you predict. It's very rare, at least in psychology, to have a universal theory of some sort of effect. There are always boundary conditions. You should not make a statement that generalizes over everything that's possible. One thing you can try to do is think, when would actually the opposite of what I'm predicting being true? McGuire challenges readers to think about the situation that every proposition is occasionally true, at least in certain contexts, viewed from certain perspectives. He calls this perspectivism. His idea is that it always depends. So whatever theory you have, it might be true, but it always depends on certain context. And he even goes as far as to say that the opposite of any theoretical prediction is also true, depending on situations. So try to define these boundary conditions and these contexts as well as possible when you make a theoretical prediction. Fiedler distinguishes between two parts in the scientific cycle: a loosening stage, where we generate theoretical ideas, and a tightening stage, where we select and test the best of these ideas. Now, when we're in the loosening stage, you have to create as much random variation as possible. Anything goes. Whatever helps you to generate good theoretical ideas goes. So you can play around with the data, explore, come up with crazy ideas, and that's all fine. Only later in the tightening stage comes the part of the process where we think, okay, which of these ideas that we generated was actually good? Which should we reject and which can we use to keep going? You can think of what a theory would really imply, come up with as many as possible ideas of what a theoretical prediction actually is when you read about something in the literature, for example. You can play around with methods. If you have some sort of measurement device, try to use it in all sorts of different ways. You can also play around with data. You might even simulate data to see what would happen depending on specific assumptions, and then subsequently use the ideas that come from these simulations to test them on people. Or you can explore existing data sets. Now, of course, we talked about how exploring data sets can increase the type 1 error rate. But here we're not talking about the testing stage, not the tightening stage of theory testing. We're talking about generating ideas, and anything goes. So if you look at data sets and you can come up with a very good theoretical prediction, that's perfectly fine. Of course, after generating this idea, you actually want to move on to the tightening stage and see whether this idea actually holds. But that's a different function. It comes later in the scientific cycle. Now, in this lecture, we've talked about generating theoretical ideas. Throughout the course, we mainly focus on drawing valid statistical inferences. But you cannot draw good statistical inferences without having a good theory. So theory construction and generating valid theoretical predictions is just as important as statistical inferences, although it might be more difficult to teach. It's important to keep in mind that a good theory and good statistical inferences are two sides of the same coin. In this lecture, we'll talk about replication studies. Replication studies, where you repeat an experiment, try to observe the same results, are a cornerstone of any empirical science. At the same time, they're quite challenging to perform, and they're not always rewarded when people perform them. When we look at the scientific literature, we see that replications are a cornerstone of any empirical science. This is nicely illustrated by this quote by Karl Popper. Now, whenever you cite Popper, people have to take you seriously, right? So let's take a look what Popper says about replication studies. He says, only when certain events recur in accordance with rules or regularities, as is the case with repeatable experiments, can our observations be tested in principle by anyone. We do not take even our own observations quite seriously or accept them as scientific observations until we have repeated and tested them. Only by such repetitions can we convince ourselves that we are dealing with events which, on account of their regularity and reproducibility, are in principle intersubjectively testable. We've been talking a lot about calculating statistics and estimating the reliability of findings, but the real test is really whether a study replicates. If someone else reproduces your study, does everything exactly the same as you did it, will they observe the same results? Now, this became a hot topic after the publication by Daryl Bem of the set of studies that examined precognition. So there's a set of studies where people are seemingly able to predict the future. And of course here, if this is a real effect, it's immensely important. If people can really predict the future, we want to know. So immediately after this publication, people set out to try to replicate these studies. This is one example of a study that tried to replicate the original observations by Daryl Bem. The title already gives it away, Failing the Future. 3 unsuccessful attempts to replicate Bem's retroactive facilitation of recall effect. So these researchers did everything more or less the same as Daryl Bem did in his original studies, but they did not observe a precognition effect. I want to point out that this publication appeared in the journal PLOS ONE. PLOS ONE is a groundbreaking journal that publishes any effect or any set of studies as long as the studies are well designed. Now you might think, what's so special about that? But it means that they also publish replication studies. Again, you might think, what's special about that? Shouldn't any scientific journal publish replication studies? But this is not the case. It turns out that these authors first submitted their replication studies to the same journal as the original study appeared in. Elliot Smith, the editor of the Journal of Personality and Social Psychology, rejected the submission. He said, "We don't want to be the journal of BEM replications." So he rejected these replication studies because he didn't want to be a journal that publishes replications. The field criticized this decision. The idea is that if replications are so important for science, then journals that publish original results should also publish well-designed and well-performed replication studies. In this publication, we see that the norms in the field are quickly evolving. This publication, Correcting the Past, Failures to Replicate Psi, is a set of studies where researchers again try to replicate the original studies by Daryl Bem, and they fail to find any effect for precognition. The only change here is that these studies appeared in the same journal where Daryl Bem published his research. We now see that many journals explicitly invite replication studies, pre-registered or not. So this is a real improvement in the recent years. People are starting to value replication studies more than they did in the past. Now, if replication studies are so important, you might think that we have a very clear set of rules of how to perform these studies. But this is not the case. How we should perform replication studies is a very active, ongoing debate in the literature at this moment. Now you might think, if these studies are so very important, why didn't we think about how to do this 100 years ago? I don't know, but now at least we are addressing the questions of how to do an adequate replication study. Now when you try to do a replication, the first thing to realize is that there is no such thing as an exact replication. You can never really repeat everything in exactly the same manner. You're studying real-life people, times are changing, there's always some minor variation. We can distinguish between a direct replication, so even though it's not identical, in this case you're trying to stick as closely as possible to the original study. You're keeping everything that you think matter the same. You can also perform a conceptual replication, or, as we might call it, a theoretical reproduction. We already see that you're not doing exactly the same in exactly the same way, but here you are testing the theoretical idea in a slightly novel way. You're changing things in the study design or in the manipulations, but you're trying to test the same underlying hypothesis. The goals of doing replication studies are many. The first is identifying type 1 errors. Now, if you've set your type 1 error rate to 5%, you'll say there is something when there is nothing, a maximum of 5% of the time in the long run. So the goal of a replication study is to identify these false positives in the literature. And this is of course very important because we want to know that the data in the published literature is reliable. The second goal is controlling for artifacts. Sometimes there might be a lack of internal validity in a study. You've used a very specific type of stimuli, for example, one set of words, and you might want to do a replication with a slightly different set of words. Or maybe you even want to use pictures instead of words. This shouldn't really matter for the basic effects, but it increases the internal validity of the study. Third goal is to generalize to new populations. One criticism in psychology, for example, is that a lot of the research that's being done is performed on students. These are typically highly educated. They come from Western democratic universities. So sometimes researchers might wonder, does this effect generalize to completely different populations? And you might want to do almost exactly the same study, but just on different culture, for example. The fourth goal is especially for conceptual replications. Here you're trying to verify the underlying hypothesis. If this prediction holds, we should also observe a slightly different effect in a slightly different study that is based on the same theoretical idea. Now it's important to perform these replication studies. You might think, why bother? Everything that's in the published literature should be extremely reliable, right? We only have a 5% type 1 error rate, so how much can be wrong? It turns out that it's quite likely that studies do not replicate. We don't know exactly how likely, but there are some examples that are reason enough to worry. For example, in preclinical cancer studies, which is a pretty serious topic. So these are studies that are trying to address new medicine for cancer research. In this field, there were some researchers who tried to replicate a set of 53 very promising but also very novel studies. Of these, only 6, 11%, could successfully be replicated. Now, this is a company trying to build on scientific research, and you know that if they succeed in replicating these studies, they will make a lot of money. But even despite their very high motivation, only 6 out of 53 studies successfully reproduced. So this is a reason to worry. In psychology, there was a large-scale replication project where 100 studies in the published literature from 2008 from 3 main journals were reproduced by over 260 different researchers working in teams. They reproduced 100 studies, and when they replicated these studies, not all of them successfully replicated. It's very difficult to say how many. It depends on the threshold that you want to define for a replication. Is this a significant effect? Is it a similar effect of a similar size? Let's take a look at the p-value distribution of the effects from the original studies and from the effects in the replication studies. On the left here we see the p-value distribution, and on the vertical axis we have the p-values ranging from 0 on the bottom to 1 on the top. Non-surprisingly, given publication bias, almost all the published studies yielded p-values that were smaller than 0.05. On the right, we see the p-value distribution in the replication studies, which are all over the place. Purely based on p-values, about 40% of the studies replicated. Again, this doesn't mean that the theory underlying these original studies is not true. A failed replication does not falsify an entire theory. There can be many reasons why a replication fails. Of course, we have to think about what these reasons could be, but it's too early to dismiss all these studies. Nevertheless, a replication rate of around 40% is not as high as you would like it to be. So which studies might be especially troubling? In a paper in 2015, Lindsley called this the troubling trio. 3 aspects of studies that should make you slightly more doubtful. The first is low power, small sample sizes. The second is a relatively high p-value, and as we saw in the lecture on p-value distributions and in the lecture on p-curve analysis, this makes sense. The last one is a surprising result, and as we saw in the lecture on Bayesian statistics, this is also a valid reason to doubt the original finding. So whenever there was a small sample size, a relatively high p-value, and a surprising result, we can refer to this as a troubling trio, and we should be slightly more skeptical about these studies, and it's definitely worthwhile to try to replicate these studies before you try to build on them. Now, in recent years, we see an increase in what you would call large-scale reproducibility projects. Meta science could rescue the replication crisis, Jonathan Schooler says here. He's referring to what's known as registered replication reports. In these studies, many different labs collaborate together and they replicate one study. So instead of the replication project where 100 studies are replicated one time, in these situations we see that many different labs replicate the same study. So now we have a huge amount of data. Let's take a look at one of these data sets, the Many Labs project, where a set of studies was replicated, and here we see what's known as a prospective meta-analysis. The researchers decided that they would combine all the studies that individual researchers did and calculate a meta-analytical effect size. So these are replications of the same study by many different labs all over the world, and if a result is statistically significant in these studies, we can be fairly confident that this is a true effect. We have so much data that these kind of replication projects really tell us something about the probability that the original study is true. Now, if you want to build on the published literature, it's always smart to perform what's known as a replication and extension study. You replicate the original result and you create some sort of addition, something new. You add a condition where you change something about the stimuli or about the manipulation. So in these cases, if the replication is successful but the extension is not successful, you have good reason to doubt the novel thing that you introduced. If you cannot reproduce the original result, you might not necessarily doubt your new idea, but you should have more doubt about the original study. If we really want to know whether results are reliable, it's essential that they can be replicated by other labs. Replication studies are a cornerstone of any empirical science. In this lecture, we'll talk about publication bias. You would hope that researchers publish all data that they collect, regardless of whether their results are statistically significant and supporting their hypothesis or not. It turns out that this is not the case, and if you do research, it's important to recognize publication bias in the literature. Now, one of the biggest problems of the over-reliance on p-values in the scientific literature is their use as a threshold to publish. People think that if a p-value is smaller than 0.05, the results are worthwhile to be published. But if the result is higher than 0.05, they often do not submit these papers for publication. As a consequence, if we plot the p-value distribution in the scientific literature, we can see that there's sort of a curve going on, as we explained in previous lectures. You can see it here by the red line. The red curve is illustrating this. And then at the threshold of 0.05, the vertical red line, we can see a huge drop. You might think that this curve should continue on, and it should, but what's indicated here is a large missing section of the scientific literature. It's like a big monster came by and bit a part out of all the p-values that should be there. So this missing part is missing due to publication bias. There are studies, but we just don't have access to them. In the scientific literature, this is known as the file drawer problem. If people perform a study and they observe a non-significant result, p-value higher than 0.05, they're less likely to submit this result for publication. Instead, they store the data in their file drawer. Nowadays, this probably would be a folder on your computer somewhere. Now, as a consequence, if you look at the published literature, most of the published results confirm the hypothesis. So, in psychology, more than 90% of published papers support the hypothesis that they set out to test. Some people have even joked that if we're so good at predicting what will happen, why do we bother collecting data anyway? If 90% of the studies that we perform support the hypothesis, then let's just skip the data collection and assume that whenever we have a good idea, it actually is supported by the data. Now, of course, this can't be the truth. This is not what's going on. We just don't have access to all the non-significant results and all the results that do not support the hypothesis. There are some reasons why people are hesitant to submit non-significant results for publication. No results are difficult to interpret. It might be that there's just no effect. It's also possible that the study you designed simply wasn't very good. Maybe there is a true effect, but you need to study it in a better way. You need to change your study design. Now we see that people might try again and again. And of course, if you take this to the extreme, and you only submit for publication the one significant result out of 20 different tries to observe something. In this extreme situation, you're only publishing no results, false positives. Now, there is random variation in studies we perform. We know this. This is a good example of what it can lead to. If we publish results, then sometimes there will be an extreme finding that shows a very strong positive effect. Sometimes there will be a finding that shows a very strong negative effect. As long as we publish all available evidence, we can do a meta-analysis that says, on average, there's really nothing going on here. But because we only publish these extreme findings, significant results in either direction, you end up with a scientific literature where everything both causes cancer and prevents cancer. So let's say that you study the amount of wine that you drink and the likelihood that you will get cancer. There will be a study that says, oh, there's a strong positive association. If you drink more wine, you are more likely to get cancer. There will also be studies that say if you drink more wine, you're less likely to get cancer. All in all, there's just nothing going on, but people are just publishing flukes, false positives on either side. And if we would have access to the entire literature, we could just say that this is just a null effect, there's just random variation around zero. Now, as long as a research area doesn't share all results, it's not a quantitative science. This is a strong statement, but really, if you want to express the evidence that's in the data, you need to have access to all the data. If you only have a subset of all the available evidence, you cannot make a good statement about what's going on. So if you want to be a quantitative science, you need to publish all data. There are some recent initiatives where people try to convince researchers to empty their file drawers. These are online databases where people can report previously unpublished results, often non-significant findings, so that the scientific community has access to all the data that has been collected. Now, it's important to realize that there can be over 200 published studies with significant p-values without there being a true effect. As long as there are thousands of people examining the same research question, and all these researchers perform multiple studies a year, then after a couple of years we'll have ended up with a literature that contains exclusively false positives. Of course, this is a very extreme situation, but it might happen. Now, publication bias cannot be corrected in a meta-analysis, but it can be detected. So you can see that it's present, and as a consequence, whenever publication bias is present in a meta-analysis, be more careful in interpreting the meta-analytic effect size estimate. In this graph, we see what's known as a funnel plot. We have simulated a large number of studies with a true effect size of a Cohen's d of 0.66. We see a vertical dotted line at the true effect size, and all the individual studies fall more or less around this true effect. On the vertical axis, we see the standard error. You can think of this as the sample size. The further we go up in the graph, the bigger the sample size becomes, and at the bottom, we have studies with very small sample sizes. Now, the gray pyramid indicates the area within which studies are not statistically significant. If a dot falls in the white area, it will be statistically significant, p-value smaller than 0.05, but if it falls within the gray pyramid, it's not statistically significant. Now, in these simulated studies, the pattern is exactly as you would expect if there's a true effect and no publication bias. But let's take a look at a meta-analysis where the meta-analytic effect size was exactly the same, but where publication bias is present. This data comes from a real meta-analysis by Hager et al. In 2010 examining ego depletion. We see that the dots are distributed in a peculiar way. They fall very close on the edge of the gray pyramid. It's almost like people were throwing these dots from the side against the gray pyramid, and they stuck exactly on the border. Of course, there's still some variation around it, but there's really a surprising number of p-values or studies very close to this border. This is an illustration of publication bias. There's some selection going on. We're missing studies that should fall within the gray pyramid, and a lot of these studies are just only on the border of the funnel plot. Now, as I said, we cannot correct for bias, but we can detect publication bias. One of the tests that we can do is a trim and fill analysis. The basic idea here is that there are certain studies that are missing, and we can fill in these missing studies based on some assumptions. So in this case, we see a lot of open circles, which are studies that are assumed to exist and are filled in the existing meta-analysis. Now, a trim and fill analysis will give you an adjusted effect size, but it's very tricky to interpret this. It's probably not correct, the adjustment might not be enough, so you can use a trim and fill analysis to say, look, there is bias in this meta-analysis, but you cannot use the adjusted effect size estimate as an indication of what the true effect size is if there would not have been bias. Another way to take a look at what the true effect size removing any bias might be is by only taking a look at the biggest studies. This is called a cumulative meta-analysis. You start with the biggest study that you have available in your set of studies in the meta-analysis, and you calculate the effect size, and then you add the second biggest, the third biggest, etc. And you only look at the effect size estimate after adding a number of really large studies. Now in this plot you can see that there's a slightly changing effect size estimate. It becomes bigger and bigger and bigger as the studies become smaller. Now this is problematic. Ideally we would see that the largest studies all sort of center around the true effect size, but even in this case, in this literature of ego depletion, the largest studies already contain some bias. Another technique you see in the published literature to detect bias is known as fail-safe N. It calculates how many studies you need with no true effect before the meta-analytic effect size is reduced to 0. It's a little bit of a peculiar measure, and even the person who originally came up with it no longer recommends people to use it. So don't use this in your own meta-analysis. A more fruitful approach might be meta-regression. In meta-regression, you draw a regression line through the studies in your meta-analysis. If you think about the funnel plot we saw earlier, it's basically a regression line where instead of each individual being a data point, now each study is an individual data point. You can use the endpoint of the regression line, where the standard error is 0, to estimate the true effect size, even though bias is present. Now, use these techniques with care, but techniques such as Egger's regression might give you an indication of the true effect size after correcting for bias. Of course, we already talked about P-curve analysis. You can complement your traditional meta-analysis and the bias detecting techniques such as meta-regression or trim and fill with a P-curve analysis. If the P-curve analysis says that there is evidential value and the bias correcting techniques all show that after correcting for bias there's reason to assume there's still a true effect, then you might conclude that the available evidence is quite reliable and supporting the hypothesis. Let's assume you perform a set of 4 studies. Each study has 80% power, which is quite reasonable. Then in this case the probability of observing exclusively significant results is 0.8 times 0.8 times 0.8 times 0.8. which is 41%. So if you perform 4 studies with 80% power in each study, the probability of finding exclusively significant results is only 41%. So most 4 study papers with 80% power should have at least 1 or 2 non-significant results. So given that non-significant studies should be expected, why don't you just publish them when they happen? One way to publish results, regardless of their significance level, is of course if you pre-register them. If you decide that a study is worthwhile to do and the reviewers agree, then they will give you an in-principle acceptance after reviewing your study design. If you follow up with the plan and you perform the study as detailed, then you can publish the results regardless of the significance level and prevent publication bias. There are now some journals that accept pre-registered reports. Comprehensive Results in Social Psychology is one. Cortex is another journal that very early started with accepting pre-registered reports. And if you're collecting data that's very difficult to collect, it's a lot of hard work, and you really want this data to reach the scientific literature, you can consider submitting to these journals. Now, if you perform a set of studies and you observe some non-significant results that you decide are not worthwhile to really discuss in detail in the methods and results section, then at the very least discuss these results in the discussion. This is really the place to say, these are some other studies that we've tried. We did not observe anything, but we think we have very good reasons why we're ignoring this data, because whatever the reason is. If you've discussed them, share the data, make it available online, let people draw their own conclusions. In this lecture we've talked about publication bias and how to detect it. I really think that publication bias is one of the biggest challenges that the scientific community needs to address in the next few years. As long as there is strong publication bias, it's impossible to have a quantitative science. So if we decide to fix one thing in science, it should really be this. In this lecture, we'll talk about open science. We see in recent years that the scientific community is moving towards more transparency and opening up all aspects of the scientific enterprise. We'll discuss what's happening and whether you want to join into this open science movement. So, open science can be divided into maybe 6 different aspects. You have open access to publications, data, materials that are used in scientific research, the peer review process, educational resources, and open source software. Let's talk about all of these in turn. First, open access to the scientific output. It might sound like it's a good idea that whenever a taxpayer pays for scientific research, this taxpayer also has access to the publications that come out of this research. Regrettably, at the moment, this is not yet the case. If someone wants to read a scientific article, he or she has to pay to get access to this article. This is not an ideal situation, and everybody agrees. We see a move towards open access, providing people with access to the scientific literature without paying. There are different models to achieve this. One is called gold open access. In this case, the researcher or the university the researcher works for have paid to provide access. Another option is green open access. Here the scientific output is still hidden behind what's known as a paywall, but a version of the publication, typically just a Word document, is available for anyone who wants to read it online. Nowadays, we even have less legal solutions to this problem. There's a website, Sci-Hub, which provides access to all the scientific literature without having to pay, but of course this is completely illegal at the moment. That such a service exists shows that there's a big problem at the moment, and I think that in a couple of years we'll see a big move towards open access and hopefully making scientific literature available to anybody who's interested in it. If you publish a scientific article, you can see whether you are actually allowed to share a preprint or a postprint, so the Word document that you submitted to the journal before publication, on a website. So you can share this version for anybody to read. So this is the green open access model. So if you visit this website, Sherpy Romeo, you can see whether you're allowed to share your scientific output. And this is always a smart thing to do. Research shows that people who put these free available versions online, the legal way, get more citations in their scientific research. So this is nice. People can read it and they'll cite it more as long as you make it available. The second point is sharing data after publication. When you do this, science becomes more reproducible. People can take your data and they can rerun the analysis that you report. They can even try out different analysis if they're interested in doing this. Data storage itself is not organized through laws. There's no law that says that you have to store your data somewhere, but it's regulated through regulations. There are very often scientific institutions, such as the Dutch Association for Universities in the Netherlands, that have guidelines and ask researchers to, for example, store their data for 10 years. Now, if you collect scientific data and you publish it, you are required to make this data available until at least 10 years after publication. So data should be made available upon request. When other people in the scientific community ask for your data, you should share this at least whenever it's legally possible. Now, if your department has no central rules for data storage, then data storage is your own responsibility. Don't store your data on the hard drive of a single laptop, or even worse, on a USB stick. The data might just disappear, the hard drive might crash, and then the data is gone. So it's your responsibility to make sure that in 5-6 years from now, people can still have access to the data that you collected. Often when you analyze data, you will also be able to provide an analysis script. When you do this, try to add comments to whatever code you use to analyze your data. This is not just useful for other people, but it will also be useful for yourself in the future, so that you can understand your own code more easily. If you create a data file, give names to the data. Provide useful names that people can understand. Again, this is useful for other people who want to look at your data later, but it's also useful for if you want to look at your own data in a couple of years. Ideally, when you publish a scientific article, you will provide the raw data, the analytic data, and the results. The raw data is the data as you collect it with whatever software or whatever questionnaires you used. Then you can typically use some sort of analysis script that transform the raw data into the analytic data. This includes removing outliers or dealing with missing data, and it might also include calculating averages from questionnaires. When you have the analytic data, then you have a second set of code that creates the results section as you write it down in your scientific article. And you might even be able to provide additional code from these results that lead to figures that you publish in the article or tables that you have produced. So in the ideal situation, the data that you share goes from the raw data to the analytic data, to the results, and then directly to the figures and the tables. So this would create a completely reproducible results section. There are some journals that require authors to make all data underlying the findings described in their manuscript fully available without restriction, with very rare exceptions. PLOS is one of the journals that does this. You might have data that's really too sensitive to share, but in most situations the expectation is that whenever someone in the scientific community asks for your data, you'll make it fully available. So it's useful to prepare a data file that can be easily shared with other people when you submit your scientific findings for publication. Many science funders now require what's known as a data management plan. Whenever they fund scientific research, they expect that the researcher that performs this research has some idea of how the data will be stored for the foreseeable future. There are all sorts of technological solutions nowadays to store data. Because we have the internet, we can share data in the cloud, and there are all sorts of services that allow you to upload data files and share them with other people. From data, we can also move on to sharing materials. If you've published something and you share all the materials that you used in your original research, this will make science much more efficient. Other people can use the same materials, either to try to replicate your result or to build on it and to test new theoretical predictions. The Open Science Framework is a free service that allows researchers to share whatever they want, materials but also data, with fellow scientists or anybody who wants access to it. On the right you see a list of files that we've shared related to a research project that we published. You can see that we share the questionnaire that we used, so other people can use the same questionnaire if they want. But we also share some sound files that were used in these studies. Of course, in the publication we try to describe the content of these sound files, but that's very difficult. And by just giving people access to the sound files that we used, we can make it as easy as possible for other people to understand what we did exactly and to build on this line of research if they want to. Nowadays, we're trying to reward these kind of practices. One example of a reward program is the use of badges. Whenever you publish research where you make data openly available, materials openly available, or where you have pre-registered your hypothesis before collecting the data, this will be clearly marked. Now, it might sound a little bit like you're back in kindergarten. Whenever you perform good behavior, you get a sticker. But making these good behaviors clearly visible is an important aspect of promoting open science. Another aspect of open science is opening the peer review process. The goal of this is to make science more transparent. We can see that some journals are now not just publishing the research itself, they also provide access to the peer review history. When an article is submitted for publications, peers evaluate the quality of the article. By giving access to the peer review history, you can see the communication between peers before the final version of the article was published. This gives more transparency to the peer review process. A final aspect that I want to mention is the use of open source software. The goal of using open source software is making data and analyses more available, more accessible to people that might not be able to buy commercially available software. For example, in this course, we rely on R, free statistical software, that anybody with access to a computer can download. If we would use commercially available statistical tools, then we would rely on people to be able to buy the software before they can follow along with assignments or sometimes with analyzing data. And this is something we want to prevent. We want to make the data as accessible as possible to as many people as possible. Another thing to keep in mind in terms of transparency is to disclose conflicts of interest. When personal interests potentially compromise scientific objectivity, you're supposed to disclose this, for example, when you're reviewing articles or when you're publishing scientific articles yourself. An example of this, where conflicts of interest were not disclosed, comes from the tobacco industry, which tried to cast doubt on smoking causing cancer by making statements such as there is no conclusive proof that smoking causes cancer. Now, of course, this first of all shows they were not really well versed in philosophy of science. We can never have conclusive proof of anything. But there was overwhelming support for the idea that there was a relationship between smoking and cancer. Of course, some researchers working for the tobacco industry did not disclose these conflicts of interest and tried to cast doubt on this relationship. This should be prevented. You might think that people want to practice open science. Why wouldn't a scientist practice open science? Well, one reason for this is that scientific research can be quite a competitive enterprise. We see that scientists try to not only further scientific research, but also further their own scientific careers. And in these aspects, sharing things like your research materials and your data with other people is not always immediately to your own benefit. We can see this as a social dilemma. If everybody would do this, science benefits. But if I don't do it, but other people do it, I benefit more because I don't have to invest anything, but I do reap the benefits. So in these social dilemmas, it's sometimes necessary to convince people to practice open science. And we see that governments, who very often fund scientific research, start to require that researchers adhere to open science principles more and more. Now, in recent years, this discussion is increasing because technology makes open science possible. It was very difficult to share your research materials or your raw data 100 years ago. But now all the technological challenges have been solved, so it's possible to do this. The question now becomes whether you're interested in adhering to these open science practices. You might either do this because your science funder requires you to follow open science principles and share all the data that was generated by tax money, for example. But you can also choose to adhere to open science principles because it's closely related to the norms and the goals that you have in doing science.